Welcome to a series of lessons on concurrency, parallelism, and non-blocking I/O. That's quite a mouthful, I know. And I know that you're as eager as I am to get to some code examples. We're going to do that, but an overview will be very helpful when we hit the code. What you're looking at in my Emacs editor is one of the working files. It's called introduction.txt, and it basically summarizes the points that we're going to cover in this lesson. But I'm not going to read this. Instead, what I want to do is a very quick demo, and I'd like to start with something that's familiar to all of us. So I have my browser open. As you can see, I'm open to the Amazon e-commerce site. And what I'm going to do, just for demo purposes, is come over here and click on this image. And as you can see, the page refreshes, of course, and in fact, I get a different page, and a lot's going on. If we reflect on this for a moment, we can see the things that had to happen in this very short time span. So the time span was, let's say, a couple of seconds. So in that time span, the browser had to respond to a user input, in this case, a mouse click. It had to do some networking, had to go off and fetch some HTML, some images, bring those down. It had to do some parsing of the HTML under the hood, build the so-called DOM, the tree structure. It had to display that tree structure and do some miscellaneous bookkeeping. For example, Amazon needs to remember the last page, the previous page, that sort of thing. So in more technical terms, there are several tasks that Amazon has to perform in the same time span, let's say a couple of seconds, and so it has to support concurrency. So concurrency in this context is simply handling multiple tasks in the same time span. Now, I have a fairly recent machine, my MacBook Pro here. It's got several processors, and what that means is that this machine can perform multiple tasks literally at the same time. In other words, this machine is capable of what I'm going to call true parallelism. So we can take the tasks that need to be done concurrently and farm each of those tasks out to a separate processor and, if possible, do all of these things at the same time. So concurrency and parallelism are related, but they're not the same thing. Concurrency, again, is handling many tasks in the same time span. Parallelism is literally processing many tasks at the same time. So let me return now to my little document. I'm going back to the Emacs editor. I've got a little summary of these points up at the top. And what I'd like to do is move down to this third bullet point and talk a little bit about it. There are two classic ways to manage concurrency. One is known as multiprocessing, the other as multithreading. For now, I'm going to depend on your intuitions. We'll quickly get to more technical definitions of these terms. Each mechanism supports true parallelism on a multiprocessor machine. So if you have more than one processor, you can do true parallelism. Now, the third component that I want to look at is non-blocking I/O, and this is probably the trickiest one to explain, but let me make a general point which is commonsensical. Of all of the operations performed on computers, I/O operations in general are the slowest. So for example, adding two numbers is relatively fast, but printing their sum to the screen or writing their sum to a file is relatively slow. The idea behind non-blocking I/O is to have a processor not wait for an I/O operation to complete, but rather to start the I/O operation, go off and do something else, and then, depending on the mechanism used, come back later to finish the I/O task. Non-blocking I/O, from a broad perspective, is a way to manage concurrency, but without parallelism. So all three of these terms are related, but they're not identical. I'd just like to make one quick point about non-blocking I/O. It's a little different than multiprocessing and multithreading in this sense. Nowadays, it's almost always used as a concurrency mechanism in conjunction with one of the other two. So for example, the Nginx web server, which is very high performance, basically uses multiprocessing to manage concurrently all of the incoming requests that it gets from clients And it also uses non-blocking I/O under the hood. And this is what gives it some of its high performance. The Node JS framework, which is responsible for a lot of the current interest in non-blocking I/O, has a non-blocking I/O at the API level, and it also has multiprocessing at the API level, but it uses multithreading under the hood. We'll see examples later that will flesh out these points. So let me try to do a quick wrap-up. Concurrency and parallelism are closely related, but not identical. On a single processor machine, you can have concurrency, but not true parallelism. The good news for all of us in the computer business nowadays is that virtually every machine that we now use is multiprocessor. For example, if you bought a smartphone within the last 5 years, you basically have a multiprocessor machine. To get a little bit into the jargon, in the bad old days, when we talked about the CPU, the central processing unit, in other words, that architectural unit that contains at least one processor, we were talking about one processor. So people would often use CPU and processor interchangeably. Nowadays, the good news is that at consumer prices, we can get a CPU that has, for example, 2, 4, 8, 16, any number of processors. These are so-called multi-core CPUs. So what we now have is lots of applications that require concurrency, and we have machines that support parallelism. Now, there are uses of parallelism beyond concurrency, and we'll get a look at those. But in the beginning, we're going to focus on concurrency as a challenge, and we're going to look at parallelism as one of the ways to meet that challenge, and non-blocking I/O as yet another way to meet that challenge. In this lesson, we're going to sharpen our definitions of concurrency and parallelism, get something a bit more technical, which is going to help us when we get to those code examples. You're looking at the working file concur_parallel.txt, and I've got some verbiage that summarizes the points, but I want to focus on the very simple pictures. So to begin, let's assume we have a web server, and we have a bunch of client requests coming in, presumably from browsers, but they could be from other applications as well. And I'm going to define task 1 as the task that handles the first request, task 2 as the task that handles the second request, and so forth. So from the perspective of the web server, each incoming request represents a task that needs to be handled in some way or other. So what I'd like to do is to contrast two scenarios. In the first scenario, we've got an old-fashioned single processor machine, so all of the tasks have to share that processor. So some sort of time slicing is in play, and I've depicted the situation as follows. I've got a time span with a start time and a finish time marked, and then I've depicted down here the processing of the two tasks. So task 1 runs for a while, in my little depiction for 8 ticks of the clock. Each star represents a single tick. Then task 2 is processed. Task 2 takes only 4 ticks. Presumably we're just delivering up a static page or something that doesn't take much time. And then task 1 resumes to, presumably, completion. So maybe task 1 has to go against a database or run some sort of script, whatever. It takes a bit longer. Now, what we have here in this first scenario is concurrency. That is, we have overlapping handling of two different tasks, 1 and 2, but there's no parallelism. So it's never the case that task 1 and task 2 are literally being handled at the same time. What we hope, of course, is that the switching between the handling of the two tasks is so quick that it simulates true parallelism. In the second scenario, you can eyeball it right away and see, of course, that there's been a boost in performance. In particular, the throughput has increased. In other words, we're now able to complete the two tasks in less time than it took before. So this is a performance gain. Now the reason, of course, is that in the second scenario, we're assuming that we have multiple processors. For this example, 2 would be enough, assuming that one task can run on one of them and another task on the other. So the depiction down here illustrates the parallelism. Task 1 goes from the start time to the finish time, but task 2, by contrast, doesn't take anywhere near that much time. What I've done, by the way, is just arbitrarily placed task 2 someplace in the time span. It could be happening right at the start with task 1, but I've shown it a little differently here. It doesn't really matter where it occurs. The important thing is that task 1 and task 2 now are being done quite literally at the same time. So in the second scenario, we again have concurrency, but we also have true parallelism, which we don't have in the first. Now this very simple example is enough, I think, for the moment. This will get us started. As we get into code examples, these technical definitions of concurrency and parallelism are going to be refined naturally. In other words, in the course of working through the code examples, we will get ever sharper understandings of concurrency and parallelism. In this lesson, I'd like to explain why various languages are going to be used in this series of lessons. So the working file you're looking at is called languages.txt, and once again, it summarizes what I'm going to cover. So let me make a very important point at the beginning. This course really doesn't assume proficiency in any particular programming language, but it does assume the ability to program. Java and C are probably the favored languages in the course, and I'm going to explain why. The main reason for using different languages is that these different languages have different approaches when it comes to doing concurrency and parallelism. So let's start with C. So C is especially important, as I note here, because the operating system libraries that all of the languages use for concurrency and parallelism, those libraries are all written basically in C. In some cases with a little bit of assembly language, but if you're not familiar with C, C compiles into assembly language, which then compiles into executable machine code. So C and assembly are quite close. So when we deal with multiprocessing, for example, I've got a little list of the sort of C library functions that we're going to be looking at. For multithreading, here's another very short list of the sort of functions that we're going to be using. And for non-blocking I/O, I've listed a few more down here as well. So C provides the underlying infrastructure for doing, in effect, concurrency, parallelism, and non-blocking I/O. It's as close to the metal as we're going to go. Let me reassure you that except near the end, we're not going to be looking at any assembly language. But when we do straight parallelism, even assembly language will have its benefits. Now, let me talk a bit about Java and C#, which are very closely related languages. In Java and C#, the preferred way to do concurrent programming is by using multithreading. Can you do multiprocessing in Java and C#? Absolutely. Have the non-blocking I/O libraries gotten better in Java and C#? Absolutely. No question about that. But the preferred mechanism for concurrency remains multithreading. So when we look at the Java examples, most of those examples are going to be multithreading examples, and a few will be non-blocking I/O examples. If you consider the dynamic languages, which have also become quite popular recently, JavaScript, I'm really thinking now here of Node JS, in other words, a full-blown JavaScript that has access to the file system and all of that good stuff. Perl, Python, Ruby, all of these really favor multiprocessing as the way to do concurrent programming, and we'll get into some of the reasons a bit later. Finally, Node JS is particularly important because it has reinvigorated interest in non-blocking I/O. It certainly didn't invent it, but it really got the attention of a lot of folks, including myself. Now, from time to time, we'll see examples in other languages as well, so I'm going to move back up just a little bit to this line. I'm going to look at examples in Go. I'll talk a little bit about Clojure, but not do any examples in Clojure. The reason Go is important is that it has emphasized new approaches, well, technically not really new. As you know, in our business, Everything is basically been done before, or at least it seems that way. So Go has revived interest in an approach taken in the early 1970s for doing concurrency. We're going to be looking in particular at Go routines and channels. It's very useful. Other languages, Java for example, has now started to copy some of the approaches that have been taken in Go. So I realize that it's going to be a bit challenging to move from one language to the other. Let me assure you, before we actually get to the code examples, that I'll explain each of them very carefully. Our interest is not going to be in the syntax, how do you do this in C, how do you do that in Java, that sort of thing. Our interest is really going to stay focused on concurrency, parallelism, and non-blocking I/O. The examples will really be helpful. They'll get us close to the metal, but we won't get distracted by syntax details. In this lesson, we're going to look at the system call and how it relates to concurrency, parallelism, and non-blocking I/O. There's an important distinction that underlies the system call. That's the distinction between user space code and kernel space code. Different terminology is sometimes used. You may hear, for example, user mode code or kernel mode code, but the essential distinction is the same, and the gist of it is the following. Ordinary applications and most standard library functions, so in other words, functions that are delivered with the operating system, Windows, Unix, Mac OS X, whatever, most of this code does not have direct control over the critical shared resources in a computer system. With respect to categories, those resources are the following: processors, memory, I/O devices. In other words, an ordinary application such as a browser cannot control the screen. That's an I/O device. Instead, the browser in effect has to make a request to the operating system to display something on the screen. Kernel space code, by contrast, consists of those critical operating system routines that control the shared resources. In other words, kernel space code you can think of as the resource management code that comes with the operating system. This code is sometimes described as being pinned to memory. In other words, when you boot up the system, the kernel space code is loaded into memory and it stays there indefinitely. You couldn't afford, for example, to have it swapped in and out. It would be far too inefficient, and besides, without that kernel space code, nothing is going to happen in any case. Now, what I'd like to do is explain how this distinction between user space and kernel space code fits into what we're doing. The topic is the system call, but I'd like to explain it with an example. Suppose we have a Node JS application. So if you've not used Node JS, it's a JavaScript dialect. And in Node JS, there's a package called cluster and a function called fork. So our Node JS app, as shown here, calls the library function, in other words, the Node JS library function, called cluster.fork. Fork is the traditional name for the function that makes a copy of the currently executing process. So we run a program, suppose this is called test.js, that runs as a process. When you call fork within that application, what you're doing in effect is cloning the current process, the currently executing application. Those details we'll return to later. What we care about is cluster.fork calls a standard library function. So for example, on a Windows machine, this would be called a Windows API function. On a Unix machine, this is described usually as a libc function, or sometimes a variant thereof, a glibc function, and so on. So there's a standard library function of the same name. The library functions, by the way, are written mostly in C, maybe with a little bit of assembly language. The library function then calls a kernel routine, in other words, a core operating system routine, and that core operating system routine has different names. In traditional Unix, for example, it's also called fork, a little confusing. In recent Linux distributions, that kernel routine has a different name. It's called clone. It's actually the function that does the heavy lifting. It's the function that actually makes the clone, makes the copy of the currently executing process. Now, the important thing from our point of view is this. The system call originates, is not made by, but originates in that Node JS application, the call to cluster.fork, and the library function fork, which is also in user space, as is the application. It's the library function fork that crosses that critical boundary that separates user space from kernel space. So the library function fork makes the system call. From our point of view, the important thing is that a system call originates in user space, it terminates in kernel space. It terminates with the execution of some critical operating system routine that has control over and manages shared resources. Again, processors, memory, I/O devices. So we're going to have occasion to talk a lot about system calls when we do multiprocessing, multithreading, and non-blocking I/O. Now, let me make two other points. The first is this. Not every library function makes a system call. For example, if you're just manipulating strings, computing their length, for example, there's a library function called strlen for string length in C. That does not make a system call. Of the 2,000 or so functions that are in a standard library, roughly speaking, 400 or so make system calls. Finally, I'd like to use this to motivate yet again the C examples. The standard libraries, the core operating system routines, are all written in C. So when you write C applications, you're about as close to the metal as you'd like to get. The only way to get any closer is to write in assembly language, which can be quite challenging. So we now have the system call out on the table, the distinction between user space and kernel space, and the system call notion and the distinction between user space and kernel space is going to prove very useful to us in the forthcoming code examples. This lesson is a wrap-up of what we've seen so far. The working file is called wrapup1.txt. So let's go back to where we began. The general topic is concurrency, parallelism, and non-blocking I/O. To begin, concurrency and parallelism are closely related but distinct. So for example, on a single processor machine, you can have concurrent applications, but you can't have parallel applications. True parallelism requires multiple processors, so you have to be able to be doing literally multiple things at the same time. Concurrency is slightly different. Concurrency means doing many things within the same time span. That would cover, of course, parallelism, but you may do one thing, switch quickly to another, switch back to the first, and so forth. So concurrency is absolutely possible on a single processor machine. The great appeal of parallelism is this. It's a natural way to do concurrency. It also is an efficient way to do concurrency because when you go parallel, what you're doing in effect is boosting performance. Since you're doing more than one thing at the same time, your throughput increases. In other words, the amount of work you get done in a given time period is going to increase. And that means, in everyday terms, higher performance. So it's a great thing. And parallelism, as we'll get back to a bit later, has become the chief approach to boosting performance nowadays. Now, there are two classic approaches to concurrency, and that is multiprocessing and multithreading. I still owe you technical definitions for both processes and threads, and I'll provide those, but right now I'm going to rely on your intuitions and your experience as programmers. So multiprocessing and multithreading are related, but they are distinct approaches. Sometimes they're used together. We'll see examples of that fairly quickly, but they are distinct. So for example, some web servers, Nginx is an example, favors multiprocessing. Other web servers, the Java-based Tomcat web server, favors multithreading. Non-blocking I/O as a concurrency mechanism is not quite on the same level. In theory, it might be a third option, but in practice, it's really emerged as an attendant to one of the other approaches. In other words, what you tend to see is multiprocessing plus non-blocking I/O, and Nginx, by the way, uses that, or, as in the case of the Node JS framework, non-blocking I/O combined with multithreading. So we'll have plenty of time to look at hybrid approaches that combine multiprocessing, multithreading, and non-blocking I/O in different ways. Now, let me get back to the summary of the languages we're going to look at, beginning with C. C is very close to the metal. The standard operating system libraries are written in C. The kernel code is written in C, perhaps with a bit of assembly. So C is as close to the metal as we'd like to get. The code is fairly reasonable. Most modern languages have copied a lot of C syntax, so even if you've not seen C before, I think you're going to find it fairly easy to read and to understand. Whatever the application language, and this is the second bullet point at the end, it's important to keep in mind that everything is going ultimately through the standard libraries, again, through C code, and from the standard libraries for the stuff we're going to be doing, into kernel code. So even if we're not writing in C, you might say we're using, in effect, C code. Now, higher level languages, Java and C#, Go, Node.js, Ruby, Python, and so forth, these languages have different styles and different strengths for managing concurrency. Java and C#, for example, favor multithreading. Perl and, for example, Ruby favor multiprocessing. We'll have time to look at examples of how languages favor a particular approach. The only thing we'd like to keep in mind right now is that different languages have different strengths when it comes to concurrency management. In this lesson, we're going to look at the all-important distinction between a process and a thread. The working file you're looking at is called processthread.txt. So to begin, the traditional and still very good definition of a process is a program in execution, but the point should be made that a process is really an abstraction. It's meant to cover all of the things that go on in a computer system when a program executes. In particular, a process as an executing program requires lots of resources. In particular, it requires, of course, at least one processor to execute the code. It requires memory to hold the instructions and the data that make up the program. And typically, but not always, it requires I/O devices. So some special purpose utility processes require, of course, a processor and memory, but they may not need any I/O devices. Now, when you execute a program from the command line, so I'm showing a Windows type example down here, hello world. When you execute that program at the command line, basically what you're doing is starting a process which then executes, in this case, to completion. The most important feature of a process from our point of view is that every process has its own address space, and that address space is made up of all of the memory locations that the process can legitimately touch. If a process goes out of bounds, on different systems you'll get different error messages, but segmentation fault is a common one. But if a process goes out of bounds, it tries to hit a memory location not within its address space. The typical result is that the operating system puts the kibosh on the process. It aborts the process immediately. The important thing about separate address spaces is that these partition processes. In their natural state, you might say, one process cannot step on the memory of another process. So there's safeguarding of memory automatically with processes. Now, the notion of a thread is more recent than that of a process, and it's a little bit trickier, and I'm going to introduce it with an example. Suppose you have a program that has 50 instructions. You could treat that program as one thread of execution consisting of 50 instructions. So a thread is just a sequence of executable instructions. A thread, by the way, is what a modern operating system, whatever the variety, will schedule on a processor. So, you could take the same program with the 50 instructions and you could break it up, for example, into 5 threads of 10 instructions apiece. That seems reasonable. You could go to the extreme and break it up into 50 threads of 1 instruction apiece, which would be quite unusual. So a thread for our purposes is just a sequence of executable instructions that can be scheduled on some processor. Now, in terms of definitions, every process has at least one thread. If a process has only one thread, it's single-threaded. If a process has more than one thread, it's multi-threaded. How exactly we partition the instructions in a process into different threads is something that we'll push back until later. We'll see lots of code examples that do this, but for now, it's the concept that's really, really important. Now, the tricky part about threads, and we'll go over this many, many times, we'll have various code examples. The tricky part about threads is that threads in the same process share the same address space. And this means that threads can touch one another or touch the memory locations accessible to one another in bad ways. When that happens, there's a nice phrase to describe it. It's called a race condition, although, as we'll see, the race is a little bit unusual. So suppose you have, in a single process, 5 threads, and each thread is executing this instruction, n equals random underscore num. That's a function that generates some random value. N is a shared memory location. Now, if all of the threads can hit this, and if all of the threads are executing at the same time, that's the visual you want to have. So we have a multiprocessor machine. The results are going to be unpredictable. Indeterminate is the term sometimes used. So a race condition is going to result. What's unusual about this race condition is that the last thread to update n is, in effect, the winner, because it's that value that's going to be the value of n. For now, the general idea of a race condition is good enough, but we'll illustrate this any number of times with code examples. So let me wrap up this introduction to threads and processes with a very simple depiction. So what I've shown at the bottom of this text file are 2 processes. I'm just calling them process 1 and process 2. Process 1 consists of 2 threads, process 2 of 3 threads, so each process is multi-threaded. I'm assuming a multiprocessor machine, so process 1 is scheduled on processor 3 in the following sense. One of its threads is scheduled on that processor. In this simple depiction, process 2 has one of its threads scheduled on processor 7. Now, if we have sufficient processors, suppose, for example, we have 8, then it's possible, of course, that all 5 threads are executing simultaneously. And this is the sort of challenge that we're going to be looking at pretty carefully. So, in summary, a modern operating system schedules a process on a processor in the sense that it schedules one of the threads in that process on a processor. Every process has its own address space. They're effectively partitioned from one another with respect to memory, but threads within a process share an address space, and a challenge for a programmer in a multi-threaded process is to coordinate the threads so that bad things don't happen. The bad things come generally in 2 flavors: race conditions, which we've seen already, and deadlock, which we'll see later. So that wraps up the first technical look at processes and threads. This is a topic to which we'll return many times, but in the future in the context mostly of examples. In this lesson, we're going to take our first look at multiprocessing in the flesh, now that we have at least working definitions for multiprocessing and multi-threading. I'm in my command line prompt on my Mac, and you can see the command cat file.txt. If you're on a Windows machine, you can use type, T-Y-P-E, instead of cat. So let me show you the contents of this file. It's a simple text file, and you can see it lists 7492 and so on. These strings are not in sorted order, so what I'm going to do now is rerun this command, and I'm going to put in a vertical bar, the so-called pipe operator, and then on the right-hand side, I'm going to put sort, and you're going to get the expected output. So on the left-hand side, cat file.txt prints out the contents line by line of that file, and the contents are then piped, that's the term used, into the sort program, and the sort puts them in lexicographical order, so basically alphabetic order. The thing that's of interest to us is that we have multiprocessing in action. There are two processes at work. On the left-hand side, there's the cat process, and on the right-hand side, there's the sort process. By the way, the sort uses blocking I/O, and so it doesn't do anything until it gets the contents of the file. It then sorts the contents of the file and prints them out to the screen. So the simple pipe at the command line is a nice example of multiprocessing at work. So let's take a closer look at the details, at what's going on here. This is one of the working files. It's called multiprocessing.txt. And what I do at the top, basically, is to repeat what I just did. So there you see the cat command. And I summarize here. The important thing is this. If we're on a machine with multiple processors, and in this case we are, what you're going to have is true multiprocessing. Here I summarize a bit how the pipe operator works. And down here is a conceptual overview of the pipe operator. So a depiction. On the left-hand side, you see a writer, so that's the right end of the pipe. The vertical bar, again, on all modern operating systems, is the pipe operator, and then on the right-hand side is the reader. By the way, in a forthcoming code example, we're going to do a pipe. This is called, by the way, an unnamed pipe. We're going to do a pipe in code. So here I summarize what's at play with the processes. So basically we have two programs in execution, in this case cat on Unix type systems, or type on a Windows system, followed by sort. Now let me generalize this a bit. When you do multiprocessing, there are two general approaches, one of which we've just seen. So in the first approach, the fork command is used. And fork is a synonym roughly for clone or spawn. You'll also hear this jargon used. What the fork does is to make a copy, a clone in other words, of a process called the parent, and the child and the parent then execute exactly the same code. As we'll see in later examples, an if-else construct or the equivalent is then used to separate what the child should do from what the parent should do. So this is a straightforward division of labor approach. It's a separation of concerns. You have one process do something and the other process do something else. The pipe then acts as a vehicle for the two processes to talk. In more technical terms, the pipe is a mechanism for inter-process communication, typically abbreviated as IPC, and we'll see quite a bit of this. The second approach is quite different but more common. In this approach, a process generates a child process, but then the parent process goes away to be replaced by the child. On Unix-type systems, and even on a Windows system, there's a family of functions called exec, and there are variations on these for execute, which allows, in effect, one process to execute another process. And we'll see code examples of this. I'd like to suggest, basically as a confirming exercise, one further little experiment. So what you see down here is something else you can type in at the command line. You see sleep 5. So the sleep process is going to sleep, in this case, for 5 seconds. And then you see the pipe operator, again, the vertical bar. So I've put my cursor over it for emphasis. And then on the right-hand side, you see echo hello world. Now what's peculiar about this example, it's contrived, as you might expect, is sleep 5 does not generate any output, so nothing goes into the pipe, in effect, and echo does not expect any input. So what happens at the command line, what you're going to see is this. You're going to see hello world pop up on the screen, the right-hand side of the pipe. That process will be operating. And then roughly 5 seconds later, you're going to get the command prompt back. So let me run that here just for emphasis and bring back my command line prompt. So I'm going to clear the screen. And I'm going to do just what I did in the handout, sleep 5, and then I'm going to do the pipe and echo. We'll just do hello to simplify this. So you can see the hello has returned immediately. That process has terminated in effect. And then you can see I got back the command line prompt because the sleep process had completed its sleeping. In this lesson, we're going to look at multithreading in action. The example is the Tomcat web server, which is written in Java, and which implements what's come to be known as the one thread per request model for handling client requests. That is, HTTP or HTTPS requests for resources that Tomcat hosts. In early versions of Tomcat, a given request would be handed off to a particular thread, and that thread would see the request through to completion. In more modern versions of Tomcat, the same thread may not see the same request through to completion, but in any case, there is always a thread dedicated to handling the request. So let's get a little into the details. Tomcat starts as a single process, and that process is multi-threaded. The number of threads involved is configurable, but nowadays it's best to let Tomcat make these decisions. Websites and web services are deployed to Tomcat as jar files. These files have a .war extension, and so they've come to be known as WAR files. So for example, if I had a website called site1, it would be deployed as the file site1.war. And deployment is fairly straightforward. There's no need for us to get into those details right now. The WAR file name is important in a client URL. So for example, you can see I've got the cursor before the line http://somemachine.org 8080. 8080 is the default port on which Tomcat listens for HTTP requests. And immediately after the port number, you see /site1/. So that /site1 represents the WAR file. Note that the .war extension is not used. So any request against that WAR file is going to be handed off to a thread. Indeed, any request for any WAR file is going to be handed off to a thread for handling. On the next line, you see a more complete URL, and at the end you see hi.jsp, and presumably this is some script that does hello world as a website. Now, here's the challenge for the programmer in basically writing websites and web services using a web server such as Tomcat. Code within the WAR file is susceptible to race conditions precisely because all of the threads to which Tomcat is delegating the request handling, all of these threads run within the same process, and so they all share the same address space. So we're back to the prominent challenge that comes with multi-threading: how to coordinate the threads appropriately so that they don't step on one another, since they all have access to exactly the same memory locations. Now, over the years, Tomcat has become increasingly sophisticated and increasingly efficient. So for efficiency, Tomcat, like any modern thread-based web server, is going to create a pool of threads at startup, and then basically take threads from that pool and delegate requests to those threads. The reason for doing this at startup is that thread creation is a relatively expensive process. Thread destruction is also relatively expensive. So what you want to do is have the threads available from the time the web server starts until the time the web server goes down, so that the cost of thread creation basically can be amortized across the lifetime of the web server. Now, Tomcat is not alone in implementing this one thread per request model. For example, there are other Java-based web servers that implement essentially the same model. Jetty is probably the best known of the alternatives to Tomcat, and other technologies as well implement this. As we'll see in a later lecture, ASP.NET implements essentially the same model as well. A final word, and this is something that we'll be looking at in more detail a bit later. Almost always in modern web servers, a hybrid approach is taken. So you might do multiprocessing plus non-blocking I/O, multithreading plus non-blocking I/O, multiprocessing plus multithreading. You might even have some combination that involves all three. So what we've looked at in this particular lecture is, you might say, a pure form of multithreading for emphasis, but not modern Tomcat, like modern web servers of different stripes, tend to use a hybrid approach. For now, however, our emphasis is on multithreading, and so that's the part that I wanted to emphasize in this lesson. In this lesson, we're going to focus on non-blocking I/O. I'm going to start with a very quick demo with JavaScript. So I have my Chrome browser open, and I have the URL set to a file called block.html. We'll look at that just in a moment, but let me run the demo now. So as you can see, a JavaScript alert pops up telling me that this is right before a blocking call. And then I get another alert notifying me that it's right after a blocking I/O call. So let me show you the HTML. You can see it consists basically of embedded JavaScript and little else. Line 3 is the critical line for us. I'll highlight it here in the browser, but we'll look at it more closely in the working file in just a moment. So you see there a call to local storage.getItem on the right-hand side, and that's a blocking I/O call. So we'll use that basically to contrast it with code that does non-blocking I/O. So let me bring up that working file. This is my Emacs editor, and the name of this file is nonblocking.txt. So let me now focus on the code that we just saw in the browser. Here it is, and it's very simple JavaScript. So let me go through this rather quickly. So at line 1, I set local storage.name. If you've not used local storage, it's basically a cache that JavaScript provides for you. .name is arbitrary. I could have called this anything, and I'm setting that to Flintstone. Then I'm doing an alert, just so it's easy to follow what's going on. And then here's the important part for us. I have a call to local storage getItem name. So I'm referring back to the key that I introduced up at line 1. And the important point for us is that nothing happens here. And what I mean by that is line 4 does not execute until local storage getItem name returns. Now it could return successfully. In this case, it's going to. It's no big deal. But either getItem is going to return with success or an error is going to be generated. In any case, the second alert is not going to execute until getItem returns one way or the other. So line 4 waits, in effect, until line 3 completes. Or in the jargon that we're using, local storage.getItem is a blocking I/O call. Now the second example is going to be in pseudocode, not in JavaScript, for technical reasons that we'll get into a bit later. So the pseudocode is straightforward. I basically define what I call callback function. It takes one argument, which is an HTTP response. We're going to assume that this is properly formatted and so forth. We don't care about the internal details. And I'm also going to assume that I have a function called extract product list from response. And what it gives me back is a product list that's appropriate for printing. And then I print it here. As you can see, my indentation is a little bit off today. So let me fix that on the fly. Okay, so callback function is going to be called from the code below. So in the pseudocode, what I do first is to set a URL to some fictitious resource. I get the connection with that URL. So again, this is just fictitious for our purposes. Our emphasis is on the blocking versus non-blocking aspect of this. And then at this line, I call fetch. What I'm doing is I'm asking the system to go off machine, to fetch some document and to return it, but I don't want to wait at the fetch line. So instead, I provide an argument, which is a callback function. So what I'm telling the runtime in effect is this: return immediately from fetch, but go off and do the fetch, and when you have something to report to me, call my callback function way up above. So again, that's the callback function. After all of that is done, we print hello world, and then for good measure, we do a second print as well. Now here's the point that I'd like to make. Here's the challenge and the complication of non-blocking I/O. It's unclear exactly what order things are going to print in. Now I'm assuming that the print hello world is blocking. In other words, nothing's going to happen until hello world appears on the screen. After that, goodbye cruel world, which is also a blocking call, is going to output that message to the screen. The real issue is, where does this print occur? Probably it's going to occur after the other two prints, because after all, we're going off machine. We have to do some processing, extract the product list from the HTTP response and so forth. But basically, this is a guess. Maybe an educated guess, you could argue, but it's still a guess. It's possible that if that URL business occurs very quickly, the connection is set up, the document is retrieved, it's possible in principle that the print product list could be the first print followed by the other two. Or it may happen that print hello world occurs followed by print product list followed by print goodbye world. So even this very first pseudocode example gives us a sense of the challenge that comes with non-blocking I/O. To be sure, there's efficiency because, for example, we call fetch, but we don't wait around for fetch to do something with success before continuing. We call fetch, we continue on our way, and then if fetch returns with success, we're able to print at some point a product list. The purpose of this lesson is to pull together various strands of the discussion that we've had so far. So we've looked at multiprocessing, multithreading, and non-blocking I/O, mostly separately, and I'm going to continue to do that in this lesson. So you're looking at the working file, 3approaches.txt, and I'm going to use once again the web server as an example, basically for two reasons. For one thing, web servers have a straightforward functionality. In other words, even if we're not experts in web servers, we all recognize that a web server has to accept an incoming client request, apply whatever application logic is appropriate to that request, and then generate a response. So this is what I mean by the straightforward functionality. More important for our purposes is that web servers have to do all of this concurrently. So no production-grade web server is going to take request 1 from start to completion, and then request 2 from start to completion, and so forth. If a web server did that, of course, a particular request may hang during processing, and everything else then would starve. In other words, the other requests would go unserviced. So web servers are a nice example. It's not that we're going to write one or anything like that right now, but we want to use them to make general points about multiprocessing, multithreading, and non-blocking I/O. So again, even though modern web servers use combinations of these concurrency approaches, I'm going to focus on each one separately in this lesson. So let's start with multiprocessing. What a production-grade web server is going to do is take an incoming request and dispatch it to a process as the request handler. And a process, again, for now, is just a program and execution. We've looked at that a little bit. We'll come back and flesh out the details later. Modern web servers that use multiprocessing are sometimes described as being pre-forking web servers. And what's meant by that is that the process pool of request handlers is built when the server first comes up. We talked about this a little bit earlier with respect to multithreading. It's the same idea with multiprocessing. You want to amortize the cost of process creation at startup. You want to amortize that cost across the lifetime of the web server. So pre-forking web servers are now the rule. In the early days, the bad old days, they were the exception. As noted a moment ago, each of the processes that acts as a request handler is in this pool. As a request comes in, it's dispatched to one of these processes, and when the process is done handling that request, it goes back into the pool. Modern examples of such web servers are Apache 2, Nginx, and IIS. There are others, and as noted, we need to come back and refine the description of Apache to Nginx and so forth, and we'll have time to do that. With multi-threading, you have a very similar approach. In other words, what now happens is at startup, the web server, Tomcat and Jetty in the Java world are perfect examples, are going to create a thread pool, either directly or by using one of the new fancy Java packages to do it for them. But the web servers are going to create a pool of request handling threads. And again, as a request comes in, it's going to be dispatched to one of these threads for treatment. When the request is completed, the thread that did the completed work is going to return back to the pool. And as just noted, of course, Tomcat and Jetty are production-grade examples. We'll also see how multi-threading works in the Windows world with ASP.NET. Non-blocking I/O is the trickiest of the three to describe in general terms, because really, non-blocking I/O tends to be used always in combination with one of the other two approaches, at least in production. So the purest example of non-blocking I/O is probably still Node JS, so I've noted that down here, but even Node JS uses multi-threading under the hood, not at the API level. So the idea behind a non-blocking I/O approach to concurrency, once again, in a web server would be this. Let's say that a client is going to send a request, and the request is rather large, and it cannot all be read. In other words, all of the bytes in the request cannot be read in one fell swoop. So a non-blocking approach is to read whatever bytes are currently available, cache those bytes, go off and do something else, for example, handle another request, and eventually come back to that incomplete request and read whatever bytes are now available, and so on until all of the request bytes have been read. At that point, the application logic is performed, and the same non-blocking behavior would take place in writing the response. So this overview brings together the disparate themes that we've been discussing so far. There's lots of technical detail, and eventually we'll get that technical detail fleshed out in code examples. For now, what I'd like to do is take a brief pause, and after the pause, we'll look at hybrid approaches to web servers. In this lesson, we're going to take a more realistic view of web servers as pieces of software that have to manage concurrency and use some combination of multiprocessing, multi-threading, and non-blocking I/O to do so. The working document is called hybrid.txt because modern web servers, in general, take a hybrid approach to managing concurrency. So let me start with the first example, which comes from the Windows world, and in particular, the ASP.NET world. Now, in a production environment, ASP.NET is going to be used in combination with a production-grade web server, and the Windows web server of choice would be IIS. So you can see it depicted here to the right on this line, and IIS accepts HTTP requests from clients, typically web browsers are involved, applies application logic if required, and then generates HTTP responses. Some requests are handled simply by IIS, that is, without any other help. So for example, if a browser should request index.html, a static HTML page, then IIS could deliver that page back. However, if a client were to request something like productlist.aspx, so IIS triggers how it handles a request on the extension in the request, and ASPX is basically an extension that identifies a website, in particular, a website that requires dynamic content. So if IIS were to receive such a request, it would forward it to a DLL, and the name of that DLL is ASP.NET_ISAPI.DLL. In effect, this is the link between IIS running as a process and various other worker processes that handle such requests. So you see the worker processes depicted below. I have worker process 1, worker process 2, and then ellipsis. because ASP.NET.DLL, so I'm just going to call this the ASP.NET runtime for convenience, it generates the required worker processes as needed. The number is configurable, that is, I could insist on a particular number, but in most production environments, if you can believe the blogs and so forth, people tend to let IIS together with ASP.NET DLL manage that on their own. Now, the worker processes represent the multiprocessing in this configuration, but there's also multithreading. By default, each of the worker processes handles 10 requests. Again, this number is configurable, so we can set it to something else, and each of those threads handles a single request. So basically, what you have, as in the Java model, you have the one thread per request model. By the way, the nice feature about keeping that number of requests per worker process fairly low is that if one of those threads should hang, for example, and the ASP.NET runtime detects that and decides that it has to kill that worker process, at most 10 requests are impacted. So it seems safe. It's a bit on the conservative side to keep that number low. But you could extend it to, for example, 50 threads per worker process, or you could go more conservative and reduce it to 2, 3, whatever. Now let's switch to a different example, multiprocessing plus non-blocking I/O, which is basically put Nginx on the map. So Nginx uses multiprocessing. It's got a master process and some other utility processes, but the two categories we care most about are the master process, which is the supervisor, and the worker processes that handle the incoming requests. The job of the master process is mostly to read configuration files at startup and also to keep an eye on the worker processes. For example, if a worker process goes down unexpectedly, if it dies, then the master process would start another. The worker processes are pooled at the start. In other words, Nginx would count as a pre-forking server. Now, in the case of Nginx, you have a fairly sophisticated approach. Nginx claims, and there's good evidence to back this up, that given the right sort of situation with relatively small incoming HTTP requests, and most of them tend to be small, in the K-byte range, not in the M-byte range, something like that. In any case, Nginx claims that a worker process using non-blocking I/O may be able to handle 1,000 or so requests concurrently. So the real power of Nginx comes in the mix between multiprocessing and non-blocking I/O. And I must confess that I'm a fan, so I like Nginx quite a bit. Now, let me drop down to the non-blocking I/O approach with multithreading under the hood, which is basically what the Node JS framework uses. Let me emphasize that the multithreading in Node JS does not appear at the API level. So if you and I are using Node JS, we don't do multithreading explicitly, but multithreading is used under the hood. Now I'm going to do a preliminary characterization of how Node JS works. You can see I have a very simple depiction here. But when you start a Node JS web server, the main job of that web server is to monitor what I'm going to call the event loop. In other words, the Node.js web server starts as a single-threaded process, and that single monitor thread looks for incoming client requests and is responsible for reading the request, performing whatever application logic is appropriate for that request, and then generating the appropriate response. Now, because it's dealing with multiple requests concurrently, that single-threaded process has to jump from one task to the other very, very quickly. The task handlers in this scenario, since we have neither multiprocessing nor multithreading at the API level, the task handlers are basically functions that are called by this single process with its single event loop monitoring thread. Now, the catch is this. Let's say that an incoming request requires that we go against a database or we go off machine to some remote web service, that we do all sorts of I/O that's fairly complicated. What Node.js does under the hood in that case is it basically creates a separate thread to handle that. And when that separate thread is done doing all the I/O work that needs to be done, it notifies the event loop monitor, and the single thread then continues to process by generating the appropriate response. So the internals of Node.js are a bit complicated because they differ sharply from what appears at the surface level. But at the surface level, the API level, Node.js is single process, single thread. This completes our overview of the concurrency mechanisms from a fairly high level. We're now going to start to get into lots and lots of code examples. I know everybody is eager for that. I am as well. But I think you'll find that these overviews, these general looks, will give us good perspective and will make it easier to get through the code examples. This lesson introduces a series of code examples. For each example, there will be two parts. First, we'll take an overview, a high-level view of what the application does, and then in the second part, we'll drill down into the code details. So we're in my Emacs editor right now, and you see the working file firstexample.txt, and we'll return to this in just a moment. But the first example does an unnamed pipe in C code, so I'd like to go back and review an example that we saw earlier. So I have a text file called file.txt. As you can see, it's got a bunch of records. Each is the name of a number. They're in unsorted order. So what I can do is pipe the cat command. On Windows, again, that would be the type command. I can pipe the output of the cat process into sort. So the vertical bar that you see on the screen, the vertical bar represents at the command line the unnamed pipe. So a pipe has a write end to the left and a read end to the right. Basically, we're going to do the comparable thing, but this time within a single program. So let me now return to the working file and basically go through the examples. I've got quite a bit of verbiage, and I'm not going to read it, of course. What I'd like to do is highlight some points. So let me jump down here. On a Unix type system, a Mac, Linux, whatever, after you've compiled the pipe example, so the source code is pipeexample.c, you would execute the program as you see here, /pipeexample. On a Windows machine, you would skip the /. Now, the important thing for us is that the pipe example program in execution is going to be the parent process. So we're going to have two processes, a parent and a child, and the parent and the child are going to communicate via an unnamed pipe. So what the parent does is call the library function fork, no arguments, and that library function in turn calls a kernel routine that does the heavy lifting. So this is a perfect example of what's known as a system call, which we reviewed a bit earlier. Now, from our perspective, the library function fork is important because it can return one of three values, and those are listed down here. -1 is a standard way for library functions to signal an error. -1 is favored because in binary, it's all ones. Now, it's not exclusively the error condition, but it's used quite a bit. And in the case of fork, -1 does signal an error. We could, by the way, get further information about the error, but it's unlikely that fork is going to return an error. One possible reason would be that the system already has too many processes running. The tricky part is the next part. Fork returns one thing to the parent and something else to the child, because fork, in effect, clones a process. So after a successful fork call, you have, in effect, two processes executing exactly the same code. So it's necessary in the code to distinguish between what part the child should play and what part the parent should play. In other words, we need a strategy to divide the labor. So 0 is always returned to the child process, and a positive integer is always returned to the parent process. That positive integer is, in fact, the child's process ID. So that's a unique number that identifies a process. And in this case, it's guaranteed to be greater than 0. We don't know exactly what it is. Probably it's going to be the process ID of the parent plus 1. In any case, the 0 versus greater than 0 test nicely separates the child and the parent. Now, let me come down and show you a code segment in C that implements this logic. So I'll rearrange a bit. So I'm going to start at this line. So you see PID underscore T. In C, that's an integer type of the right size. So on some machines it might be 64 bits, on other machines it might be 32 bits. By using PID underscore T, we don't have to worry about our platform. So I've defined a variable called PID, and I've set that to the return value of the library function fork. I now have the 3 tests that I talked about. If the PID is -1, we have an error condition, we need to do something. Probably we're just going to exit. If we can't fork the child, then there's no point in going on. But again, depending on the application, we might have some different strategy. The else if clause right here tests for the child, and as you can see, I've got ellipses down there in a block. So in effect, this would be the code that the child would execute. And finally, down here in the else clause, we've got the code that the parent would execute. Notice, by the way, thank goodness this is pseudocode, because up here, I just noticed it, I am missing a brace, so I hope you'll excuse me as I add it in there right now. In the real code, as you'll see, we'll be able to compile and run it with success. Now, let me make one final point about this example. What's going to happen is that the parent is going to write some bytes to the unnamed pipe, and the child is going to read those bytes from that pipe. So that's how the communication between the two is going to occur. Now we have a tricky situation. When a parent process forks a child process, and the child process dies, the operating system notifies the parent as to that fact. So what happens if the parent exits before the child? You've got a problem, and that problem has a quaint name in operating systems. The child is then known as a zombie process. The child itself dies, but the parent has not been notified because the parent is already dead. So the zombie hangs around, in effect, takes up some system resources, not a lot, but some. So we want to ensure, in this example, that the parent waits until the child has exited. And the parent is going to do that by calling another library function called, nicely, wait. So that wraps up the overview of the code. What we'll do in the next lesson is look at the actual code. In this lesson, we're going to focus on the source code for the first coding example in multiprocessing, and that's the example that implements an unnamed pipe. So we're going to look at this code in just a moment. In my Emacs editor, you can see the source code. The working file is called pipeexample.c. And what I'm going to do is compile and then run it. So first let me show you. It's in my current directory. And the compile command, gcc for the compiler, -o for output, pipeexample. We could call it anything, of course, pipeexample.c. So I'll compile, and then I'll execute. Again, on a Windows machine, you wouldn't need the // at the beginning. So here we go. As you can see, there's a single line of output. The output is actually generated byte by byte by the child process, and we'll see that now by returning to the Emacs editor. Recall that no background in C is assumed in this series, so I'm not going to dwell on the syntax, and you're free to contact me if you have questions about the syntax, but I'm going to take a high-level view, and I'm going to focus on the parts that are really important to us. So let me explain these two so-called macros in C. So they're just symbolic constants. Read end is 0, write end is 1. These are indexes into an array. So the way we're going to create an unnamed pipe, is as an array of what C calls file descriptors. Just as a process has a numeric ID, which identifies it, the process ID, so an open file has a file descriptor, which is also a numeric value. When you have an unnamed pipe, you need two IDs, one for the write end, one for the read end. So the read end is 0 and the write end is 1. Down here at line 2, report and die is just a utility function. If something goes wrong, in this case, if the fork call fails, we call report and die, it prints out an error message, and then the program executes because there's no point in going on. Line 3 are our pipe file descriptors. So it's an array of two integers. Each one of those is going to identify one side of the pipe. What I'm going to write is this string, but the important thing to note is this. This is the winter of our discontent, is basically encoded in ASCII in C. So each of those characters is a single 8-bit byte. And as you're going to see in a moment, one process is going to write the bytes to the pipe, and the other process is going to read the bytes from the pipe. So we're really working at a low level, at the byte level here. Line 4 is the critical call. There's a library function called pipe. It creates an unnamed pipe. We feed it as an argument the array of file descriptors, and if we get less than 0, in effect -1, we have an error, and in that case, we're done. Otherwise, we continue down to line 5, which is the all-important call to the library function fork. So I've changed the code slightly. I now call the variable CPID for child process ID, because that's the value I'm going to use for testing. The thing to remember is, if we get to line 5, then creating the pipe has worked, so far, so good. We now need to see if the call to fork is going to work. So the next line checks that. Again, in case of error, fork is going to return -1, so we check for that. If that happens again, we're out of business. Otherwise, we now have a typical separation of concerns pattern. So fork returns 0 to the child, so I handle that in the if clause. The child immediately closes the write end of the pipe because the child is going to act as the reader. Obviously, we could have done it either way, but in this case, the parent's going to write, the child's going to read. So the child closes the end of the pipe that it doesn't need. It then goes into a while loop, and basically what it does is it calls the library function read. In this case, read is going to read 1 byte at a time. The third argument to read, the 1, means how many bytes to read at one time. So it's going to read until it hits end of file. In this case, end of pipe. And the child is going to echo each of those bytes to the screen, and that's what it does with the write call, which is also low level. And the write call in this case is writing a single byte at a time. So we're going really low level. Once the child is done, for good practice, it closes the read end of the pipe, the end that it was using, and then it calls this library function _exit 0. In C, 0 represents normal termination. And the _exit is a special version of exit, which means, in effect, exit right away and signal the parent right away that I'm going away. So this is to prevent the zombie business that we talked about before. So the child process is effectively the reader. The else clause represents the code that the parent continues to exit. So it's very similar in spirit. The first thing the parent does is to close the read end of the pipe because the parent is the writer, not the reader. I've simplified the parent in a bit. The parent writes all of the bytes in the string at once. It then closes its end, and here's the important part. The parent then calls wait. The argument 0 here basically means wait indefinitely. Wait for the child to die. And once the child dies, the parent proceeds to exit itself. So the wait is what prevents the zombie process problem. Now let me make one last point about this code. All of the I/O operations used here, the read and the write and so forth, are blocking. The unnamed pipe, you might say, is an inherently blocking mechanism. The reader, which conceptually is on the right-hand side, in other words, when you do an unnamed pipe from the command line, you use the vertical bar, and the reader is on the right. The reader basically blocks until the bytes are available to be read. And I'm following that practice in this code. So, in summary, what we have is a single program, pipeexample.c, but it's a program that generates a process by a call to fork. And the process that's generated, the child, is a clone of the parent. The two, after the fork, execute exactly the same code. So in particular, line 6. And then we use an if-else construct, the if at 7, the else at 13, in order to divide the labor. So the child does the if part, the reading, and the parent does the write part, the writing. As a very simple and quick exercise, by the way, you could reverse the roles of the parent and child, and you'd see that the program would still work just fine. This lesson focuses on a second coding example. The second example resembles the first in some respects, but differs from it in other respects. Let me give you the details. In the first example, we had multiprocessing, and it involved a parent and a child process. So the child was a clone of the parent, cloned using the library function fork. In this example, by contrast, the two processes are in effect siblings. There's no parent-child relationship between the two. Now for the similarity. In the first example, the two processes communicated by using an unnamed pipe. In this example, they're going to communicate by using a named pipe. So there's library support for both types of pipe, and we'll get into the details in just a moment. A named pipe is sometimes called a FIFO, for first in, first out, because the named pipe guarantees that sort of behavior. That is, whatever the writer writes to the pipe first is going to be read by the reader first. And I've got a very simple depiction of that down below. So the writer is writing to a FIFO, in effect a queue, and the reader is reading from that. Now I said in effect a queue because at the implementation level there's going to be a file, as we'll see. And this file is going to be opened by, in this case, the writer, and also by the reader, and then eventually closed by both, and then dispensed with. And we'll get into those details when we see the code. Now, named pipes are very similar to another construct that you may have run into, and that construct is called the Unix domain socket, sometimes also called a local socket. So, for example, on a Unix-type system, you might communicate with a database system through a Unix domain socket, sometimes abbreviated as a UDS. It's a very common means of communication. Windows does not technically have Unix domain sockets. You wouldn't expect it to, but Windows does support named pipes, and named pipes and local sockets are very similar. It's fair to say, I think, that the local socket has a slightly richer API, but in terms of intended functionality, they're the same. A network socket is a mechanism for interprocess communication between processes on different machines, different hosts. A named pipe and a local socket is intended to support IPC among processes on the same machine, on the same host. Now let's get into some details of the example. So there are two programs. One is called the FIFO writer, the other called the FIFO reader. They're both going to be launched from the command line. I show the commands here down below. The ampersand at the end of this first command is going to run the FIFO writer in the background so that I can get the command prompt back to launch the FIFO reader. The I/O under the hood is going to be blocking. In other words, the writer is going to write, in this example, some randomly generated integers, and then the reader is going to read those integers until it encounters end of file. So, in summary, there are going to be two separate processes executing. There's no parent-child relationship between the two. FIFO writer and FIFO reader. The FIFO writer is going to write values to the FIFO. The reader is then going to read those until end of file. Now, one thing I want to point out, in case you're not familiar with C, writing to a named pipe is no different than writing to an ordinary disk file. So one of the things that C does very nicely is it blurs the differences among, for example, FIFOs and sockets and ordinary disk files. The read-write operations are essentially the same. The I/O is essentially the same. So this is a great convenience to programmers. So that's an overview of the second multiprocessing example. After a brief pause, we'll get a look at the source code. In this lesson, we're going to focus on the source code for the second multiprocessing example. This is the example that involves a named pipe. So in my Emacs editor, you're looking at the writer. FIFO-writer.c is the name of the file. And in a bit, we'll look at the other program, FIFO-reader.c. But first, let's go to the command line just to make sure that things are working. So you can see I'm ready to launch the FIFO writer. And again, the ampersand means run that in the background so that I can run the reader. And as you can see, the reader has printed out a bunch of numeric values. These are randomly generated numbers, 256 in all. And at the end, both the FIFO writer and the FIFO reader have terminated. So let's go back to the editor to get a look at how this works. As you can see, it's a relatively short program. This is appealing because it's pretty easy to use named pipes. So this macro, where I have the cursor place, max writes, is just there for convenience. I'm going to generate 256 values and write those to the FIFO. At this line, I have a name. Any name would do. And the library function of interest is this one, mk for make FIFO. It takes two arguments, the name of the file, and then that second argument is an octal, 666. This is basically the file access permissions. At the next line, we use the standard IO open function, another library function, to open up the file. And as you can see, there are some flags here in the second argument. Create is intuitive, I think. It basically means if the file doesn't exist already, create it. And the second one is open it for write only. What's returned from this is a file descriptor. I could check this to see if there was an error, but I'm being overly confident here, and I'm not performing that check. In case of an error, FD, the file descriptor, would have a value of -1. Then down at line 3, we go into a loop, and basically what happens is a randomly generated integer is captured in n, and that value is then written to the FIFO. When we get done, we close the file and we do an unlink. The unlink basically notifies the operating system that it can get rid of that underlying file when we're all done. Now the reader is going to have to unlink as well in order for the file to go away. So let's go over to the reader, which is even shorter than the writer. So you can see one thing we have to agree on both sides, reader and writer, is the name of the FIFO. So in this case, it's just called mypipe1. In this case, the reader is going to open the FIFO for reading only, as you'd expect. It's the writer that creates the file. The reader just reads from it. The reader has no idea how many things are going to be written. There could be a few, there could be many. So it goes into a while loop, and basically it reads until end of file, and then it prints each of those values to the screen, basically to confirm that everything is going okay. The file descriptor is closed on the reader side and unlinked as well, and when both sides have unlinked, then the operating system removes the file. Now, let me return to the writer momentarily to make one last point. The reason this coordinates so well is back up at line 2. In the case of a FIFO, the open call blocks on the writer side until the reader actually accesses the FIFO. In other words, nothing happens. nothing is written to the FIFO until there's at least one reader in position to read what the writer is going to put in the FIFO. So there's automatic coordination, you might say, at the library level. So this completes the look at the second example. The code is short and sweet, and both files are included, of course, among the working files. In this lesson, we're going to take another look at the Nginx web server. It's an excellent piece of software. It's written in C, and it employs a mix of multiprocessing and non-blocking I/O in order to handle concurrency. What I'd like to do throughout these lessons is jump between very specific code examples that allows us to drill into the details, but then to balance that with a broad look at how these technologies are used in production-grade software. So Nginx is an excellent multiprocessing web server. It gives us a chance in looking at Nginx to gain a broader perspective of how multiprocessing is used. So let me make a couple points, and then we'll look at some configuration and other information about Nginx. So Nginx, like other production-grade web servers that use multiprocessing, Apache 2 would be another example, are so-called pre-forking servers. At startup, Nginx creates a number of processes. There's a master process and some worker processes. There's also a couple of other utility processes that I'm not going to cover today. In any case, all of these processes are created at startup so that the cost of process creation, again, is amortized over the entire life of the web server. Now, Nginx can be and typically is started as a system service at boot time, and it should be emphasized that it's platform neutral. It's relatively easy to install. You can install it on any Unix type system or Windows, and there are various ways to do it, including a very simple way. You can download the most recent source code, for example, and build it from scratch. What I'd like to do is focus a bit on the configuration file, and you see a slice of that configuration file here. The file is called nginx.conf, and much to my delight, I must confess, Nginx does not use XML as a configuration language. Instead, it uses very simple key-value pairs. Each pair is terminated with a semicolon, so it looks in effect like variable declarations to a programmer. And some of these key-value pairs occur in blocks. So down here is an example with events, and I'll come back to that momentarily. So basically, let me describe the little slice that you're looking at here. By the way, these entries could occur in any order. So the user key and the name www/data is the first key value pair in this example. www/data is going to be the process name for each of the workers. To put it more technically, that name is the owner of the worker processes, and we'll see that in more detail momentarily. The number of worker processes is set here to 4. If you wanted to take a more sophisticated approach, you might set that number to the number of processors available on the host machine. But Nginx is very powerful, and 4 worker processes is in effect the default. You see this configuration quite often. This third entry has a key of PID, of course for process ID, and the value is the name of a file. This is on a Linux system. It's the name of the file that contains the process ID. So this is going to be used during startup. Now this next block contains information about so-called events, and the very first entry specifies how many connections are going to be allowed per worker. And the load you can see here is quite impressive. Nginx is confident that each worker process can handle 1024. So basically 1,000 or so client requests at the same time. The non-blocking I/O is what allows this to happen, because each of those worker processes is going to skip basically very nimbly and quickly from one request to another. It's not going to wait basically on any I/O event. Now this last entry gives me some system information about Nginx. So PS, process status, and there's a flag -EF. This does some formatting. And you'll notice I'm using an unnamed pipe here. I'm sending this through grep for grab regular expression. So basically what I'm asking for is information about Nginx. And I get a little tabular display if you've not seen this before. So the owner of the process ID, that's the PID, and the PPID is the parent process ID. And then the last column you can see is the Nginx process type. So I added that basically for readability. So the owner of the master process is root, superuser basically in Windows terms. And you can see the process ID. In this case, it happens to be 1803. The parent process ID is 1. Traditionally on Unix type systems, 1 is the ID of the init process, which is the first user space process that the operating system forks during boot. So basically, Nginx has init as a parent, and init, if you, for example, close the machine down, init is going to be responsible for making sure that all of its children, including Nginx, exit in a clean way. So this is the master process. The master process has very specific and in fact limited responsibilities. It reads, for example, the configuration file, nginx.conf, that we looked at earlier. It also monitors the worker processes. So for example, if a worker process hangs for some reason or goes down unexpectedly for some reason, the master process is responsible for taking the appropriate action. So for example, if a worker process goes down, then the master process is going to create another process to take its place. Over here to the right is the program that was launched. So conceptually, you could think of this as a command line entry. That program is in the user sbin directory, and the name of that program, as you would expect, is Nginx. So the master process was basically started by that process. And then, as you can confirm by eyeballing, the other processes shown here, the workers, the owner is the www/data seen earlier. And you can see that the process IDs 1804, 1805, 1807, 1808. Notice they're not purely in sequence. However, they're very close to the process ID of their parent, in this case root, at 1803. And again, by eyeballing, it's obvious that each of the workers has the master as a parent. Now, in handling client requests, it's the worker processes that come into play and not the master process at all. In other words, the requests basically flow into the worker processes, and the worker processes then use the non-blocking I/O to handle each request. These worker processes are never killed. Instead, when they're done doing a job, they're put into a quiescent state, and basically they wait then for the next job. So this overview represents a look at how multiprocessing can be used in a production environment, and we'll have occasion to look at other examples as well. In this lesson, we're going to look at another way in which one executing program can start another. What you see in the Emacs editor is the working file exec_overview.txt, and I'll explain the choice of the term exec in a moment. Under the first bullet point, you see a depiction of the library function fork, which we've seen in the two code examples so far. And the way fork works is you have a parent process, which calls fork, which creates, on a successful call, a child process, and the child is a clone of the parent. So we've seen that example in action. When the fork is called, both the parent and the child continue to execute, so something has to be done in the code to determine which part of the code the parent is going to execute and which part the child is going to execute. The alternative way involves a family of functions which begin with the term exec, E-X-E-C, and all of the functions in this family make the same system call. So basically, the underlying kernel routine is the same for all of them, but they vary a little bit in style, as we'll see. Now, in the case of exec, there's a difference. You have a process which starts out, it calls exec, And if this is successful, a second process begins, but the difference now is this. In effect, the second process replaces the first. So unlike the fork example, you don't have two processes continuing. Exec, put differently, does not do a clone. It starts another process, but it does not clone the original process that calls exec. These points can be clarified by using a familiar system term, I'm guessing, and that's image. So an image in this context is just an executable program. And in the examples we've seen so far, for example, the pipe example, the FIFO examples, we were dealing with different images. So the compiled pipe example code is an image. Now, in the exec family, basically what happens is the image that calls exec is replaced by an altogether new and different image in the normal case. So let me come down to this bullet point and review again at the code level the differences. So returning to the fork example, we have the parent process call fork. Fork returns an integer value, and we basically need to determine from that integer value which code the child should execute and which code the parent should execute. So just to review, fork returns -1 in case of error. It returns 0 to the child. So the if clause here basically asks, are you the child? If so, execute this block. And fork returns the child's process ID to the parent, and that process ID is guaranteed to be greater than 0. So it's always a positive integer. Now in the exec function, something different happens. Basically, what exec does is loads into memory an altogether new image, and then starts executing that image and terminates the currently executing image. In other words, it terminates the program that calls exec. So in this little code depiction, you see one variant in the exec family. This function is called execcl for list, and we call execcl, and the arguments are the following. The first is the path to the compiled program, so I'm assuming this is called my game. By convention, the first argument is the name of the program. I'm following that convention here, my game, and the 0 at the end basically means we're at the end of the list, that's it, there are no other arguments. In case of an error, we get back -1, as we've seen quite a bit so far. Otherwise, what happens is the following. The new image begins executing. It's got its own address space, it's got other features that distinguish it, and the function, the program that called exec basically is terminated automatically. We don't have to do anything, we don't have to do any explicit waiting or anything like that. The system basically manages all of that. Now there is some carryover. For example, the new process inherits the process ID by default of the program that exec'd it, and it also has the same parent process ID. If you wanted, you could change these. There are library functions that allow you to change a process ID and so on, but in the default case, the simple case, the new image inherits the process ID of the old image. This little overview will help us now when we get to the actual code example, so now's a good time to take a short pause. In this example, we're going to look at the source code that illustrates the library function execv. So this is one of those functions in the exec family of functions. You can see that the source code is fairly short. The comments are almost as long as the source code itself. And the file is called execing.c. It's included in the working files. So basically what the program does is the following. The source code you see below this line is going to call execv, and it's going to launch another program called file status. Let's move to the command line quickly so I can illustrate how this works. So to begin, I'm going to run file status on its own, and it expects a command line argument, a single one. In this case, I'm giving it tmp, which is a subdirectory which contains a very small file. And as you can see, what file status does, true to its name, is it prints some metadata about the file. So for example, it tells me the owner ID and the group ID, the byte size, very small, the time the file was last accessed, the type of file, this is a directory as opposed, for example, to a regular file, and it also tells me that this directory is owner-readable and owner-writable. Those would be default properties. I can also run, by the way, file status on the compiled version of the program, so basically on itself. And as you can see here, I get different information. The main difference is the file type is now changed to regular. So let me clear the screen. What I'm now going to do is run the Execing program, which is going to call the file status program, and it's going to call it with temp hardwired as the file to provide information about. So as you can see, we get a screen very similar to what we saw earlier. In fact, just for emphasis, let me run it again. And if you eyeball this, you'll see that the two outputs are the same. Now, let's return back to the Emacs editor so we can get a sense of how this program works. So some lines of the source code are far less important than others. I'm going to go over those fairly quickly. Once again, our goal is not to learn C, but to learn how these all-important library functions operate. So what I'm creating here on this particular line basically is an array of strings. So the first string is the name of the image, so I'm going to use the technical term, the executable program, and that's file status. The second argument is the name of the file that we want information about. This happens to be a directory, but it could be any file. And the 0 at the end basically terminates the array. So if you're a C programmer, that 0 is an easy way to write null. The next line is the critical one. This is where I call exec v. V is for vector. Earlier, we saw an example with exec L. L is for list. So exec v takes two arguments, the name of the image, that's the first argument, and an array, which is null terminated in C jargon, and that's the second argument. So as usual, in C, what we want to do is check to see that everything worked. If not, basically what I do is exit. A negative value indicates abnormal termination. I have an else here with a print statement, but this print statement never executes because if the exec v works successfully, then the current image, the compiled version of this program, stops executing and we never get to the print statement. And in fact, if I go back just one more time for illustration and confirmation, let me clear the screen and let me now rerun this. As you can see, that print statement, I'm here, never executes because the execing image has been terminated. It's been replaced by file status. In summary then, the use of a function in the exec family is an alternative to using fork. You have different ways for one program in execution, one process to spawn another. And we've looked at, in effect, the two principal ones. We've looked at fork, in which you have the parent-child relationship, and then exec, in which you have one image replacing another. In this lesson, we're going to focus on how the operating system keeps track of processes, and this will lead to the all-important notion of the context switch. So more about the context switch in a bit. There is lots and lots of information in this handout. I hope you can use it as a review. I'm not going to go through every item, but I'd like to begin by going through some of the things we've seen already and expanding on those points a little bit. So every process has a so-called PID, process ID, and this is a non-negative integer that identifies it uniquely to the operating system. There are library functions called getPID and getPPID for parent ID that allow you to retrieve the ID for any process and its parent. There are two PIDs that are traditionally assigned to special processes. 0 is typically reserved for what is called the idle process. In other words, conceptually, this would be the process that is executing when there's nothing else ready to execute. The init process, which traditionally has a PID of 1, is the first user space process that the operating system starts when the system boots. So the init process is, in effect, the ancestor of all of the user space processes, including all of the applications that you and I write and run on a system. When the system shuts down, by the way, the init process waits for all of its children and all of their children and so forth, so that there are no zombie processes created. And the init process does basically the heavy lifting during system boot. Now, let's get to the process context. So the context means a collection of information that basically characterizes the process to the operating system. There's lots of auxiliary information, but there are three main data structures. So let me go through these a little bit more carefully. The process table contains per process information, and this information is critical when a process is running on a processor, gets kicked off because it's exceeded its time slice, and then gets rescheduled. The information that the operating system needs to restart the process is contained in the process table. There's lots of other auxiliary information in that table as well. The page tables are really important because the page tables basically implement the separate address spaces per process. The role of the page table is to translate so-called virtual addresses or logical addresses into actual memory addresses. Exactly how that occurs isn't so important to us, but what is important is that each process is isolated within its own address space precisely because each process has its own page tables. Finally, the file table tracks, again on a per-process basis, any file that a process has opened. It should be emphasized that more than one process may open the same file. So, for example, we saw the FIFO reader and the FIFO writer when we were doing the named pipe example. Each of those separate processes opened up the same pipe. So there would have been two entries for that file. It was called pipe 1. The name isn't so important, but there would have been two entries in the file table for that. Now, not so important for our purposes, every process has a user and a group owner, and we've seen that a little bit, for example, with Nginx. Every process also belongs to a process group. Again, that's not the most important piece of information for us right now. Now, let me start to get into the context. So, modern operating systems all employ preemptive scheduling of one type or another. The particular algorithm may differ. For example, modern Linux systems tend to have a fairly sophisticated scheduling algorithm, but everybody does preemptive scheduling, and the core idea is straightforward. A process is given a time slice. It may be fixed, it may be variable, to run on a processor. If the process has not completed when its time slice has expired, then the operating system kicks the process off the processor and gives the processor to a different process. So that's the idea behind preemption. Now, the process context is all of the information in effect that the operating system has to keep in mind when it performs a context switch. The same goes, by the way, for threads, and I'll come back to this point in just a moment. So to repeat, the process context has information or contains information about the process that's critical for the operating system's management of the process. And the three principal data structures are, again, the process table, the file table, and the all-important page tables. Now, context switching is tricky, and the phrase context switch is vague. Sometimes it means process-level context switch, sometimes it means thread-level context switch. When it means, for example, going from one thread of execution to another, because we know basically that modern operating systems schedule at the thread level. So to repeat, to schedule a process is to schedule one of the threads within that process. So thread level context switching is sometimes called intra-process switching. I'm going to use the term thread level context switching to make sure that there's no confusion. Going from one process to another is sometimes called interprocess switching, but again, I'm going to prefer the phrase process-level context switching so that there's no confusion. Now, here's the idea. I'm going to jump down to this summary section. I've got two scenarios, and here's the idea. I've got process 1, which is multi-threaded. It has thread 1.1 and thread 1.2. And process 2, which is single-threaded, it has only thread 2.1. And we're going to focus on processor 7. So I want to consider two scenarios. In the first scenario, thread 1.1 is currently executing on processor 7. So process 1 has one of its threads executing on that processor. Thread 1.2 replaces thread 1.1. So that's a so-called thread-level context switch. On modern systems, the cost of that context switch is negligible. It's almost zero. In other words, it's enormously fast and efficient. The second scenario is a bit trickier. In this scenario, thread 2.1 from process 2 replaces thread 1.1 from process 1. In other words, what we have is a process-level context switch. This has high overhead. This is very expensive. It's difficult to give a general number for what a process-level context switch costs, but ballpark, and this may be even a little bit optimistic, ballpark is between, let's say, 5 to 15 milliseconds. It's going to depend a lot on the particular system, on what's going on in the process, but that's a sort of rule of thumb. So one of the downsides, in fact, you can argue the principal downside of process-level context switching is exactly that. It is the cost of doing that. Now, this has been a lot of information with respect to a summary of what we've seen so far and an expansion on those key ideas. But again, the main point behind this working file, it's called processtracking.txt, is to give you a reference document so that if you need to go back and look at some of this jargon or refresh some of these key ideas, those are presented here. In this lesson, we're going to look at another multiprocessing example, but this time in Node JS rather than in C. In the documentation right at the start, I show how to execute this program. So the name of the program is nodecluster.js. This is included among the working files, and it's the file we're looking at in the Emacs editor. And if you don't have Node.js installed, this is the URL where you can get it. Node.js is implemented in C++, and so the underlying implementation is very close to the standard libraries that are called for multiprocessing. Just in case you've not seen Node.js before, you see right at the top of the program 3 require statements. Require cluster, require HTTP, require OS. The require statement, so the require call, is used to load a package. So basically, we're using the cluster package, the HTTP package, and the OS package that come with Node.js. The cluster package up here contains the multiprocessing API. Down here, var processors, we're going to set that variable to the number of processors available on the current machine. The port number is set here to 8888, easy to remember, and this port number is not in use on the machine. All of the worker processes that are forked are going to be listening on this port. So basically, the idea here is we're going to create a multiprocessing web server that distributes the load among worker processes, all of which listen on the same port. So it's very convenient. You recall from the C examples that one of the challenges in calling the library function fork is this: fork clones. So after the fork succeeds, we have a parent process and a child process executing the same code, so we need to divide the labor. And the typical way to do that is with an if-else or comparable programming construct. In this case, I'm going to use an if-else because Node makes it very convenient. So you can see here at line 2, in the cluster package, there's a Boolean value called isMaster. This basically identifies the master or parent process. So if we're the parent process, we write out a couple of messages. We confirm the port, in this case 8888. And I'll run this program shortly, so we'll see the actual output and the processor count. In other words, how many processors are available on this particular host. Once that's done, the real work occurs in this for loop. So the for loop iterates through the number of processors and it creates a child process for each of those. So you can see at line 3, the call is to cluster.fork. That's a very thin wrapper over the standard library function, which in turn calls the kernel routine, which does the work. This next line identifies a callback function and associates that callback function with a particular event. So here's the strategy. We don't want to get lost in the syntax. In the case one of the worker processes, one of the child processes should exit for whatever reason. So you see cluster.onExit. That's the condition we're concerned about. We want the system to call this function, which takes 3 arguments. In this particular case, I don't use any of those arguments, but I could. All I do instead is fork a replacement. So the idea is, let's say we start out with 8 worker processes. One of them happens to die. We're telling the system, in effect, create a replacement. The else clause is for the workers. So what each of the workers does is creates a server associated with the same port number, 8888. And in this particular case, all that's going to happen is this. The workers are going to wait for client requests coming in. That's the listen down here. And what they're going to do is respond with an OK, and they're going to echo information that comes with the request. So this is a very simple echo server. We don't care about the web server part of it. We really care about the multiprocessing part. So that's the source code, very short and sweet. As you can see, it's a high-level API, very attractive. Let me now go to the command line so that I can demo. So I'm in my bash shell and I'm ready to go. So I'm calling node.cluster.js, the source code we just looked at. And as you can see, these are the 2 console log statements executing, listening on port 8888. And the processor count on this particular machine is 8. Now let me switch over to another shell. And what I'm going to do is use the curl utility to run a very quick test. So I'm going to send a GET request to localhost 8888, and the so-called URI, or sometimes this is called the resource path, is just /hi/world, and I get back this echoed response, confirming that this is the URI that was received. So in summary, Node.js has very nice high-level support for multiprocessing, but even in this high-level API, you can see the connection to the underlying standard library that contains the fork function. In this lesson, we're going to focus on a key challenge in multiprocessing. This is a challenge we've talked about a little bit, but we've not really emphasized it. So let me recall the pipe examples. On the pipe examples, one process generates input for the other process. So the 2 processes obviously have to coordinate. They have to communicate. They have to share information. The reason this is a challenge is that a process, by its very nature, is isolated from other processes. This is a result of each process having its own address space. In other words, processes don't share memory locations by default, so there has to be some other way for the processes to share information. Now, the sharing of information occurs through what is known generically as interprocess communication, or IPC for short, and there are various mechanisms for doing this. Some of them we've seen. I've listed the main ones in this review sheet. It's called ipc.txt. That's what we're looking at in my Emacs editor. And I'm going to go through them in no particular order, but I'm going to include the pipe examples even though we've covered those pretty thoroughly. So let me begin with what is probably the simplest mechanism. One process can send a signal to another. A signal is a very, very simple command. The API, however, is a bit complicated. It's not the cleanest API you've ever seen. But to give an example, one process can send a kill signal to another process. There are also user-defined signals, and we'll see an example of those later. Among the IPC mechanisms, I think it's fair to say that the signal is at the base level. It's the simplest, it's the most primitive, it's the least flexible. A second mechanism sometimes gets looked down upon a little bit. It's the local file, and by extension, a remote file. But let's focus for now on a local file. So you can have a local disk file, for example, that one process writes to and another process reads from. In the case of a named pipe, this is actually what's going on under the hood. But we could use local files explicitly. The file API on all modern systems is rich enough to allow locking. So, for example, we could prevent one process writing to a file at the same time that another process is trying to read from that file. So we could do synchronization at the file level. But local files used explicitly are a very basic but also highly flexible way for processes to communicate. The pipe examples we've seen so far are very close functionally to shared files. So we've seen both the unnamed pipe and the named pipe in particular, because as we saw in the FIFO examples, named pipes are implemented basically as temporary files. One nice thing about a named pipe is that it has persistence. An unnamed pipe does not have persistence. An unnamed pipe exists only when one process is writing to it and another is reading from it. Closely associated with named pipes are so-called sockets. So let me give a slightly formal definition of a socket to begin. It's a communications endpoint, and it's associated with a particular protocol. So for example, if you have a networking background, you're familiar with UDP, the User Data Protocol, and TCP, the Transmission Control Protocol. So for example, you can have UDP sockets and TCP sockets. We're not going to get into the differences between those two right now. So network sockets allow processes on different hosts to communicate. Local sockets, sometimes called Unix domain sockets, allow processes on the same host to communicate. And as noted earlier, it's very common, for example, for database systems to communicate with client applications through Unix domain sockets if those systems happen to be on a Unix-type machine. A socket, in particular a local socket, is very, very close in terms of functionality to a named pipe, but I think it's fair to say that a socket has a slightly richer API. But named pipes and sockets are close cousins. Message queues are a really powerful, persistent, and asynchronous mechanism for communication. So let me explain the asynchronous part. It's possible to set up a message queue, and it has persistence. The system maintains that, ensures it, basically. And you could have one process writing to the queue even though nobody is currently reading from the queue. In the case of pipes, that was not the case. In other words, if you go back and look at the FIFO examples, the open calls are basically synchronized together. They block, and it's not until both sides of the pipe, so to speak, open up the pipe that anything happens. This is not the case in a message queue. So I could have a producer process writing things to the queue. I could have a consumer process reading stuff from the queue, and either one of those processes could start first, and neither one of them relies essentially on the other. Of course, a reader won't have anything to read until a writer has written something to the queue. But the message queue is powerful. It adds some functionality over and above what you see even in a named pipe. Finally, there's shared memory. This is reasonably straightforward. We'll actually see an example of this IPC mechanism and some of the others mentioned as well. But shared memory allows two processes, which normally operate in completely separate address spaces, to share a memory location. So for example, one process can write something to that memory location, and then another process could read from that memory location. I think you'll find that the API is fairly simple and straightforward. And the next example we'll see will actually be a shared memory example. So this overview is a very quick glance at the various IPC mechanisms. We'll have an opportunity in forthcoming examples to flesh out some details. This lesson introduces a multiprocessing example in which two processes communicate with one another through shared memory. So we're going to look at shared memory as an IPC mechanism. Here's a simple depiction of what's going to happen. One process is going to allocate a shared memory segment. We'll see the API in just a moment, and it's going to place a string there. And then a second process is going to edit that string to confirm that the two processes do indeed have access to exactly the same memory location. So with multi-threading, shared memory is the rule. With multiprocessing, shared memory is the exception, so we have to do something to make it happen. Now, shared memory has some nice features to it. The most significant is probably this. Access is significantly faster to shared memory, because it is memory, than it would be, for example, to a shared disk file. Now let's look at the API. Here's the idea. One of the processes in this example, the putter, in effect, is going to allocate the shared memory segment and specify how big it should be. So this is fairly low level. We specify the size in bytes. Now, if we wanted, for example, if we were on a small platform working in an embedded system or something like that, we could actually specify the memory address that the kernel should use to allocate the memory segment. But in this case, we're going to let the operating system make that decision. So this is basically step one, allocate the memory. And then step two is to attach that allocated memory to the process's own address space. And this is what provides the actual access. As you'll see, this is going to be fairly straightforward as well. We can specify permissions, read, write, execute, that sort of thing. Now, the main functions that come into play here are these two library functions, shmget for shared memory get, and shmat for shared memory attach. As we're going to see momentarily, each of those takes 3 arguments, but they're fairly straightforward. So let's look at the first of the two processes by considering the source code. This is going to be the putter. So the name of this C file is putmem.c, and most of the work is done in a utility function called setup that you see at line 1. So setup takes 3 arguments. Let me go over those quickly. The key, the first argument, is an integer value that uniquely identifies the memory segment. This is a user-supplied key, so I'm going to use 9876. It's an easy enough number to remember. The second argument is the byte count, so we have to tell the system exactly how many bytes we want. Normally, as you'd expect, this is probably going to be a power of 2, but any number will do. And this is going to determine largely whether we get the segment. For example, if we request too big a segment, we might not get it. The system may not be able to supply it. And the third argument consists of flags. So for example, for the putter, the flags are going to say, create the memory segment, and here are the access rights. And they're going to be read-write. So here are the 2 calls. shmget takes 3 arguments, as noted, the key, the byte count, and the flags. And we get back an integer value. You've seen this song and dance several times now. In case of failure, we get back -1. In that case, the program's just going to die because there's nothing else to do. If that's successful, then we call shmat for attach. We provide the memory ID returned from shmget. The second argument I've set to null, 0 in C, and this says in effect to the system, you pick the starting address, I don't care, and there are no more optional flags to provide. So we're just going to go with what we have. If this succeeds, we get back in C syntax a pointer to a char, and a char in C is 1 8-bit byte. So we're basically getting back a pointer to the first byte that was allocated. Conceptually then, the memory segment is an array of bytes, and we can use it in any way we like. So again, I check for errors. If everything is okay, I return that pointer. Now down here, I create a greeting, so a string. Keep in mind that in C, these characters are ASCII codes, so 7-bit, but in effect 8-bit codes. Here I compute the length. That's going to give me the total number of bytes that I want. Here's the user-supplied key. I call setup. The third argument, again, consists of logically ORed, bitwise ORed, I should say, flags. Create the memory segment, and 0666 is basically read-write access. I copy the greeting, the bytes in other words, into that memory segment. And then this next part is a bit contrived. In order to confirm that another process is going to be able to access this memory segment, I'm going to go to sleep until the H in hello is changed to lowercase. And the editing process, as you might guess, is going to make that change. Once that happens, we exit the loop, we print out a message to confirm, and we're done. So we've seen the overview. We've seen the putter in this shared memory example. What we'll do in the next lesson is look at the editor, and I'll also demo. In this lesson, we're going to finish up the shared memory example. Let's go back and review the source code that we looked at last time. So this is putmem.c. It's among the working files. It can be compiled and run in the usual way. So the main function is setup. You see my cursor here placed on the line. And the two key calls are these. They're library functions. shmget for shared memory get takes 3 arguments. A user-defined key. It's an integer value basically, and it uniquely defines the shared memory that we're asking for, should we get it. There's a byte count, so how many bytes we want, and various flags. In the putmem program, those flags include a signal to create the shared memory and other values to determine the access rights. So basically, this memory is going to be created, and it's going to be readable and writable, but not executable. The second call is to shmat for shared memory attach. We're basically asking the system to make the allocated memory part of our address space. And this then allows the process to access that memory. So that's the setup. And it's called from main with the appropriate keys down here at this line. After that, we copy some bytes. It happens to be a string greeting, hello world bang. We copy those bytes into the shared memory. And then, for demonstration purposes, we go into a while loop until the capital H in hello world is changed to a lowercase h. And that's going to be done by the other program, and we're going to look at that other program right now. So we're now looking at editmem.c, and you see once again setup. It's exactly the same function as before. The only difference is that it's called with slightly different arguments. The editmem program doesn't create the shared memory, it simply accesses it. So there's no need to do a create. Other than that, the song and dance is pretty much the same. There's a call to shared memory get. In effect, this is requesting access to memory that some other process has allocated, and that of course was putmem. And then there's the call to attach that referenced memory to editmem's address space so that something can be done with it. Now I'm going to move down to main, and main is short and sweet. There's not very much here at all. For clarity, I set a length variable to 14. That's the number of bytes in hello world bang. In C, a string is an array of characters, so an array of bytes terminated with a null character, so that 14 includes room for the null character at the end. And that \0 character is an 8-bit 0. So it's the 0 character as an ASCII code. It's a non-printing character. Now the important thing is the call to setup. So we call setup with the same user-defined key as before, 9876. We provide the length, and then octal 6666 is the access rights. And the next line is the critical one. This is typical C. We're dereferencing a pointer. We're basically saying go to where that pointer points and set the character there to lowercase h. So in this case, we're changing the uppercase h to a lowercase h, and then just for confirmation, printing it out, and then exiting. Now let me make a general point. EditMem doesn't really know how much memory PutMem has allocated. It better have been at least 14 bytes, or we're going to have a problem, but it could have been several thousand bytes. And all EditMem is doing is asking for access to those allocated bytes and then making a change. The advantage of this approach, just to review, for interprocess communication is that we're using memory, so this is going to be very fast. We could, of course, communicate through a disk file or some of the other mechanisms we've seen, but communicating through shared memory is very, very efficient. Now, let me demo these programs for you for proof of concept. So I'm at a bash shell. I've already compiled PutMem. I'm about to run it. So I run it. It simply sits there. It's allocated the memory, and it's now doing this sleep of 1 second, checking to see if the capital H has been changed, going back to sleep, and so forth. I'll now come over to another shell, and I've compiled editmem. I'm ready to go. So I'm going to run editmem. And for confirmation, you can see that we now have hello world with a lowercase h. And if I return to that other shell, you can see that PutMem has broken out of its while loop, and it now prints hello world as well. So the change has taken, and the two processes have talked in a very minor way in this example, but they've talked through shared memory. Now that both programs have exited, the shared memory can be recovered by the system. So, to wrap up, shared memory has a pretty straightforward API. Just to review one last time, it involves, in effect, two calls, one to shmget and a second one to shmat. Each of those library functions takes 3 arguments. There's nothing very tricky about this, but it really is a very powerful mechanism for interprocess communication. In this lesson, we're going to look at the local socket, also known as the Unix domain socket, as yet another mechanism for interprocess communication. The example I'm going to use is depicted here, so let me go through the parts briefly, and then we'll talk about the interaction. Nginx we've seen already. It's a production-grade web server. The piece we haven't seen is the Unicorn application server, and that's depicted to the right with Unicorn workers. I'll talk about the workers in just a second. Unicorn is an application server that is designed for Rails applications. Basically, Unicorn is software that embeds the Rails framework, so Unicorn knows about Rails in general, although it doesn't know anything about particular Rails applications. So as an application server, Unicorn supports one or more deployed Rails applications. We're interested, of course, in the interaction among these pieces. By the way, in a development environment, Unicorn also can be used as a lightweight web server, but in a production environment, it's likely to be used in conjunction with a web server such as Nginx. Now, the immediate challenge is this. Nginx, as we know, is multiprocessed. Nginx has workers which receive HTTP requests. Unicorn is also an example of multiprocessing in action. It has processes as workers as well. So the challenge basically is for Nginx to take an HTTP request and to pass it on to one of the Unicorn workers. And in this example, we're going to do that with a local socket, a so-called Unix domain socket. An alternative approach, again, might be a named pipe, but we're going to use the local socket. The Unicorn worker that gets the request will then pass it on to the appropriate functions in the Rails app, and after Rails has done its thing, the response will come back to the Unicorn worker, back through the local socket, back to Nginx, and back to the client that initiated the request to begin. So I have some of those points summarized down here under architectural pieces. What we want to focus on is the role of the local socket, and as just depicted, what the local socket does is it enables inter-process communication, pure and simple. In this case, it's between an Nginx worker process and a Unicorn worker process. Now, this point has been made a couple of times, but it deserves to be made yet again. The question comes up, why a local socket? Why not just a named pipe? Local sockets have a slightly richer API than named pipes. They're a bit more flexible, and you'll see a lot of software prefers them. So, for example, Unicorn in Nginx is a perfect example. Unicorn makes it easy to talk to it through local sockets. If we were going to use a named pipe, it would require a bit more work. Now let's look at the low-level details, the configuration files that enable all of this to work. On the Unicorn side, the configuration file is very simple. The main line is shown here. You see listen, and then you see a string representation of the local socket. This is basically the ID, if you like, of the local socket. And then you see a comma followed by backlog 1024. 1024 is the maximum number of connections that Unicorn is going to support at a time. Unicorn basically, through this configuration file, creates the local socket. In other words, when Unicorn starts, the local socket is created, and it can be accessed through this file, /var/run, blah, 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 unicorn.sock. On the Nginx side, we also need a slightly richer configuration than we've seen before, because Nginx is going to operate as what is sometimes called a reverse proxy server. That's quite a mouthful, but let me explain the basic idea. So once again, worker processes are set to 4. There's also the master process and some other utility processes. The worker connections are limited to roughly 1,000 apiece, and the new configuration begins in this block labeled HTTP. The important point is this. Inside the HTTP block, you see the cursor is placed at the upstream app server block. The name app server is arbitrary. Upstream is a keyword. And the basic idea here is that we specify that file that was set up in the Unicorn configuration. In other words, the var run unicorn unicorn.sock. So Nginx knows from this line where to find the ID for the local socket. Nginx, in other words, is now in position to communicate with Unicorn through this local socket. In the server block, some of this information is the same as before. We're going to listen on port 80. That's the standard port for a web server. The server name is simply localhost, and the location basically is the /. So after the port number, the path, the resource location, you'll hear different phrases used. The more technical one would be URI. The URI begins with the / following the port number in a URL. And there's some pieces of information here about how the proxy server is to operate, but the important one for us is the last entry, proxy_pass, and then you see http://app server. This basically tells Nginx, when you get a request, take that request and pass it off to Unicorn. Unicorn will do whatever is appropriate. In this case, pass it off to the Rails app, and all communication will occur through the local socket, the Unix domain socket. So the configuration is a little bit wordy, but the underlying ideas are pretty straightforward. This is a nice, I think, commercial example of how local sockets can be used to support interprocess communication, and in this case, it's between a production-grade web server, Nginx, and a production-grade Rails application server, in this case, Unicorn. This lesson presents an overview of 3 longer code examples. The working file you're looking at in my Emacs editor is serversoverview.txt, and in the working files, there's a zip called servercode.zip, and I'll get to the content of that zip file in just a moment. Let me start out with the motivation behind these examples. We're going to be examining 3 general approaches to concurrent programming. One approach centers on multiprocessing, one on multithreading, one on non-blocking I/O. So the idea is to present a slightly longer code example that exemplifies features of each. The first example we'll be looking at will be a multiprocessing web server. The second will be a multithreading web server, and the third will be a non-blocking I/O web server. The multiprocessing example we'll see in the next lesson. The other two we'll see later on in this series of lessons. So let me talk about servercode.zip, the zip file that I just mentioned, talk a little bit about the contents, and also talk about the gotchas. So there's a README, which explains how to use the second entry, a makefile. A makefile is a very easy way to compile a bunch of C programs. So at the command line, if you have the make utility, and you do on a Linux or a Mac, so basically on any Unix type system, you would just type make in the same directory that the makefile occurs. We're not going to look at all of the examples in the zip file. I've included, for contrast, an iterative server which does no concurrency whatsoever. And I've also included a web client, so you can use this web client to go against an arbitrary website or even web service, and I've put that in there just to illustrate the API. The three main examples of interest to us are the forking server, which uses multiprocessing, the threading server, which uses multithreading, and the polling server, which uses non-blocking I/O. The polling server is the trickiest of the three because I use a library called epoll, which is available on Linux systems. Unfortunately, it's not available on a Mac. There is a closely related library called KQ, which is available on a Mac, and the README has a bit more information about that. This file, utils.c, contains common code for all of the server, and I'll get to that in just a moment. And utils.h is basically the same. It's a so-called header file that has code that's shared among the examples. So what I'd like to do is talk a little bit about utils.c, and then in the next lesson we'll get into the multiprocessing web server. So utils.c handles basically the networking stuff, and it performs what socket people call the three-step. It does a create, so it creates a socket. That's very much like creating a file. The API is essentially the same. It binds that socket to a particular port, and then it starts the socket listening for client connections. So I give a little bit of an elaboration down below. This code is not of particular interest to us. We're going to regard it as infrastructure. Later on, we will have an occasion to look at sockets, including non-blocking sockets, and we'll be doing that with a Java example. But for the present, the focus is going to be on the multiprocessing, the multithreading, and the non-blocking I/O. To sum up, servercode.zip contains a README, a makefile, and all of the source code that we're going to be examining. And in the next lesson, we'll start with the multiprocessing example. In this lesson, we're going to look at the first of the three web servers. This is the Multiprocessing Web Server. The full code is included in the zip servercode.zip, and the source file is called forking_server.c. In my Emacs editor, you're looking at an abbreviated version of that file. This is called forking_server_short.c. I've eliminated the includes and some other code in order to make the main code more readable. So let's begin with line 1. Here's a call to signal. This is, of course, the library function discussed earlier, and signals are a way for one process to communicate with another. In this particular case, the idea is to avoid zombie processes. Recall that when a child process terminates, the system notifies the parent. What line 1 says in effect is this: the signal that the child sends is of no interest to us. So the second argument is sig_ignore. If we cared about that signal, we could specify a function for the system to call, in other words, a callback. But to make things cleaner and simpler, we're simply going to ignore those signals altogether. The next line of interest for us is line 2. you see a call here to create server socket. The argument, false, means give us a regular old blocking socket. If we wanted a non-blocking socket, we'd change that argument to true. Create server socket is going to return a file descriptor for the socket. I call the variable here simply sock. And you'll see in a moment that we're going to use that file descriptor to await client connections. So at line 3, this would be pretty much standard practice. We go into an infinite loop. We're simply going to wait indefinitely for client connections and client requests, and we're going to handle each of the requests that we get. The accept function, the library function accept, takes 3 arguments. The file descriptor for the socket, created above at line 2, information about the client, that's going to be filled out by the system, and then the length of that data structure that contains the client information. The important point for us is that accept blocks until there is a client connecting, at which point it returns, and the variable client contains another file descriptor value, in this case, the descriptor for a socket that allows read-write operations. So a client connects, and when the client connects, there's a socket connection established between the client and the server so that they can communicate. Now line 4 simply prints to the screen certain information about the connected client, and now we get into the real point of interest, the multiprocessing. So we've seen the fork call any number of times now. So we call fork. The strategy here is let's create a process that's going to be a client handler. So that process is going to take over the work of managing this particular client. Once again, we check for errors, and if there is an error, there's not much we can do about it. We don't have a process to handle this client. Once again, we need to distinguish between the parent process, which is calling fork, and the child process, which is spawned through the call to fork. So in this case, we're getting the child. So if the process ID is 0, that's what's returned from fork to the child process. What we do is close the listening socket. So this is typical separation of concerns. The parent process is going to await client connections, and then the spawned child process is going to do the read-write operations. So the child is not going to listen for connections, so we close that socket. Down here at line 8, we call receive. This is a variation on read to read the client request. This is a blocking call. We check on how many bytes were read to make sure that there's no error condition. And then down here at line 10, we send a response to the client. The bookkeeping details are not so important to us. The idea is what the child process does is reads the client request, generates an appropriate response, and sends that response back. Once all of that is done, we close the client connection. In effect, we're now finished with that client. In a commercial situation, of course, that connection might be kept open because the conversation would be ongoing. Here, the conversation is very simple. The client sends a request, we respond, that's it. And at this point, the client handling child process terminates. This, of course, is inefficient because what we're doing on every single client connection is forking a process, handling the client, and then terminating that process. In a commercial version of this, we would want to create a pool of processes that we could reuse. In other words, we'd want a pre-forking server. Right now, our interest, of course, is on the API. The else clause is the parent code, and notice this is very simple. All the parent does is close the read-write socket that connects the server to the client because the parent process listens for client connections but does not perform any read or write operations. So this is, again, the division of labor. The child does one thing, the parent does something else. Now, let me demo this for you. So I'm going to go out to my bash shell. I've compiled the server, and I'm now going to run it. So you can see the server is awaiting requests on port 3000. I'm going to open up another bash shell, and I'm going to use the curl utility for convenience to connect. And as you can see, when I connect, I get back an echoed response. Basically, it shows what the HTTP request looked like. Let me do it once more. I'll change things up. I'll take the query string off, and I can do it a third time. And once again, you see that I'm getting the response echoed. If I go back to that original bash shell, you can see that I'm getting confirmations logged to the screen about who connected from where. So the client is connecting from localhost, that's 127.0.0.1. In summary, the forking server, which does multiprocessing to handle concurrency, illustrates the general approach, the division of labor between the parent process that awaits connections and the child processes that handle the individual requests. It does all of this using multiprocessing. The chief inefficiency is that fork is called continually, the child process does its thing, and then it terminates. We'd like to eliminate that and basically create all of the child processes at the beginning, put them to sleep, and then use them as needed. So that concludes our look at the first of these servers. We'll be looking at the other two in due course. Now is a good time to take a short break. This lesson introduces a pair of exercises that you're welcome to try. One exercise involves some programming, the other does not. I'm going to run the source code that you see in the Emacs editor momentarily, but let me go through it first. The file is called exercisemp.c, and the MP, of course, is for multiprocessing. So line 1 we've seen before. This call to the library function signal tells the operating system that we don't care about receiving signals about the termination of a child process, because of course there's about to be a call to fork. Line 2 is more important for us. So there's an integer variable n initialized to 777. The important point is that the child process is going to inherit its own copy of n. So there's going to be two copies of n, the parent copy and the child copy. So there's a printout of the initial value, just to make this easy to follow. At line 3, the fork call. So we clone a process. Line 4, we check as usual to see if this succeeded. If not, we're out of business. And here, the familiar if-else construct to separate the code that the parent should execute from the code that the child should execute. So in this case, the child executes the if clause and the parent executes the else clause. The child increments n by 10, in other words, increments its own copy of n by 10, and the parent decrements its copy of n by 10, and then each process prints out the results. So the question is the print order determined? In other words, when we run this, what we're going to see is a particular order, and the question becomes, must that order always be followed? Could it differ on a different platform? Could it differ on a different run on the same platform? So let me run the code very quickly. I'm in my bash shell. I've already compiled, and I do an execution. You can see initial value, 777. The sub 10 is printed first, 767, and the incremented is printed next, 787. So in this particular run, it's the child process that printed first, followed by the parent process. So could it occur the other way? Could it be initial value, followed by add 10, followed by sub 10? Now let me return to the editor. So this first exercise doesn't require any programming, but it does require a fairly solid understanding of how multiprocessing works. So the second exercise is more ambitious, and the idea here is to take the forking server, which we've seen. The code again is in the zip file servercode.zip. It's to take that forking server and to amend it by making it a pre-forking server. As you'll recall, in the current forking server, every time a client connects to the server, there's a fork. The forked child process then handles the client, but once that handling of the client is over, the child process is terminated. So those are expensive operations. the fork call to spawn a new, in effect, request handler, and then the exit call to terminate that request handler. The idea is we'd like to create a pool of worker processes when the web server first starts, and then put those processes into a wait state. As clients connect, we would then take a process out of the wait state and have it handle the client. After the handling of the client is over, we're going to put it back into the wait state. So the suggestion that I would make, this is a challenging exercise, the suggestion that I would make would be to implement a queue and basically have the waiting processes in the queue, and then when a client handling process is required, use a signal to wake up the first process in the queue. So there's some queue management, and there's also some signaling that come into play. As noted, the second exercise is a challenging one. The Signal API in C is not the friendliest thing that you'll ever run across. But if you can get this done, well, congratulations, it's a job well done. In this lesson, we're going to take stock of multiprocessing as a concurrency mechanism. Multiprocessing has other uses, but our interest right now is in multiprocessing as one of the ways to manage concurrency. What I'd like to do is to contrast the upsides and the downsides of multiprocessing. This won't be an exhaustive list on either front, of course, but the main points deserve to be brought to the forefront so we can keep them in mind as we move towards multi-threading and then non-blocking I/O. From a programmer's perspective, the greatest appeal of multiprocessing is, I think, that it's the operating system, not the programmer, who needs to coordinate memory access. In other words, because every process is by default insulated within its own address space, the programmer does not have to worry about race conditions when doing multiprocessing programming. It's the operating system that makes sure that no two processes step on the same memory locations. Unless, of course, the programmer decides to use shared memory as an interprocess communication device. And we've seen an example of that. But you can look at it this way. It's the offloading of responsibility from the programmer to the operating system that's so appealing about multiprocessing. Now, on modern systems, and in particular, I think it's fair to say Unix-type systems, process creation is relatively efficient, but it's certainly not cost-free. And this theme will come up again when we look at multi-threading. There are ways, of course, we've seen this with pre-forking web servers. There are ways to amortize the costs of process creation and process termination across the lifetime of an application. And there are various things that can be done to make the cost of multiprocessing as low as possible. It's also possible to take processes and put them in a quiet state, a wait state if you like, and to use signals to wake them up when needed. Now, because processes are, by their very nature, isolated from one another, each in its own address space, the question arises, how can processes coordinate on a common task? And this brings to the forefront the idea of interprocess communication. How can processes share information? There's a variety of ways of doing so there's great flexibility here. We've seen signals, we've talked about disk files, local and even remote. We've seen examples of named and unnamed pipes. We've seen local sockets in action and even remote sockets in the web server example. Although we didn't focus on that API, we will have occasion to do that later. There are message queues and, of course, shared memory. So there's a rich assortment of ways for processes to work together if they need to do so on a common task. Now let's talk about the downsides. The biggest downside is, I think, the efficiency one. In other words, a process-level context switch, when one process loses a processor to another because the operating system does preemption. So this is a so-called interprocess context switch. This is relatively expensive. As noted earlier, it's hard to put an exact figure on the cost, but the cost is in the millisecond range. And this is fairly expensive when you think that modern computers, even everyday devices, have clock speeds in the half a nanosecond range. So context switches are absolutely a non-trivial cost. If you're going to do multiprocessing, it's something that you need to be concerned about. The reason for that cost is that when a context switch occurs, the operating system has to do a fair amount of bookkeeping. Most of that bookkeeping has to do with the process and page tables. The details don't concern us so much, it's the overall cost of doing that. Now, this cost is offset to some degree by advances in modern systems and process scheduling algorithms, and system administrators can also do a nice job, for example, of setting time slices, if the operating system supports that sort of thing, and trying to keep the number of processes basically in line with the number of processors available on the system. In other words, to do some sort of coordination between those two. There are, again, library APIs for putting processes in a quiet state if we need to, so we can try to cut down, again, the overall cost of creating and terminating processes. Let me end with a couple of points. Multiprocessing is sometimes looked down upon as old hat or ancient history, and that, I think, is a mistake. For large software projects, for example, database management systems, web servers, multiprocessing is still widely used. And there's lots of programming experience within our community with multiprocessing. It's been around for a long time. So I think, like everything else in programming, this is something that should be put in the toolkit and used when appropriate. So multiprocessing is not the hot new topic, that's for sure, but it's certainly a tool that should be in every programmer's toolkit. This lesson focuses on multithreading and presents an overview that will be useful in the programming examples to follow. You're looking at the working file multithreadingoverview.txt in my Emacs editor. So let's begin with a contrast of multithreading and multiprocessing, since we recently finished up the wrap-up of multiprocessing. And let me present the contrast in terms of upsides and downsides with respect to multithreading. So the chief advantage or upside of multithreading over multiprocessing is that threads are inherently lighter than processes, and this has some nice results. At the most obvious level, on a modern system, a process is a collection of one or more threads, so the parts, of course, are lighter weight than the whole, than the collection. It's this second sub-bullet that really deserves emphasis. A thread-level context switch. So a thread is executing on a processor, its time slice expires, the system kicks it off and puts another thread on that processor. A thread-level context switch has a near zero cost on modern systems. By contrast, a process-level context switch has a significant cost. It's someplace in the millisecond range. So thread switching is very fast. Process-level context switching is relatively slow. Now, let's get to the chief disadvantage, and this really has to do with threads within the same process. Because threads within a process, as noted before a couple of times, share the same address space. So two threads of execution in the same process can literally access the same memory location at the same time on a multiprocessor machine. The upshot is that it's the programmer rather than the operating system that must ensure that this doesn't happen. So in a multi-threading program, the programmer takes on a lot of responsibility. The programmer is responsible, in short, for coordinating threads so that they never access the same memory location in an inappropriate fashion. In other words, in the jargon, the programmer must ensure that there's no race condition. Now, the catch is this. So I'm going to move down to this third sub-bullet. The catch is that thread coordination is really tricky business. You've got to do it just right. If you do too little thread coordination, you open up the threat of race conditions and unpredictable results. In other words, if there's a race condition, we don't know what the value of a given memory location is going to be. So that's where the unpredictability comes in. If you do too much thread coordination, you hurt the efficiency of the running application, and you may even bring about deadlock. And we'll see deadlock in a code example in a bit. Now, let me make a couple of general points, just background points. They're not absolutely essential to what we're doing, but they do provide some good foundational knowledge. Although every modern system schedules at the thread level, in other words, to schedule a process is to schedule one of the threads in that process, systems have different implementations of threads. So, for example, modern Linux systems tend to implement threads as processes that happen to share an address space. So, under the hood, the implementation is really just the traditional Unix process implementation. Other systems, Windows is a nice example, actually provide kernel-level support for threads as opposed to processes. The difference for us doesn't really matter. At the API level, in terms of the behavior of threads within an executing application, we get the same result. In other words, threads within a process share an address space. Threads in different processes have different address spaces. Now, the forthcoming code examples are mostly in C and Java. There are some code examples in Go as well, for contrast. C and C# are very close in their threading APIs, although again, people in both camps may be offended by that claim. I'm going to use Java as an example of a system that handles concurrency mostly through multithreading. So in the Java world, it's clear that multithreading is the preferred mechanism for handling concurrency. In any case, we'll get a variety of code examples. The early examples will be in C and Java. This lesson analyzes a Java program that deliberately creates a race condition. You're looking in my Emacs editor at racec.java, and this is the working file. And at the top, I've got the first two lines to explain how to compile and run. If you're not familiar with Java, but I assume that most people have some background there. So the compilation command is javac, racec.java, and then the execution command is java main. Now, I'd like to introduce some jargon for convenience. When the Java program executes, the main function in the class main begins execution, and I'm going to refer to the thread that executes that code, the code in the main method, as the main thread. This is for convenience. So the program starts out single-threaded, and that single thread is the main thread. The main thread then creates two other threads, and the object references are T1 and T2. But I want to deliberately blur the distinction between the object reference and the thread to which it refers. In other words, instead of saying over and over again the thread to which T1 points or something like that, I'm simply going to say thread T1. So after the main thread creates threads T1 and T2 and starts those threads, we now have a multi-threaded program. In particular, the application is responsible for three threads, main, T1, and T2. In terms of flow of control, what the main thread does is this. It creates T1 and T2 by calling the constructor. We'll see that momentarily. And then the important thing is this. The main thread calls start on T1 and T2. Start basically registers these threads with the Java runtime, and when those threads execute, in other words, when they're scheduled on a processor, the system calls the run method that's encapsulated in each thread. So, in fussy terms, it's the instructions in run that constitute the thread, because you'll recall that a thread is a sequence of executable instructions. So all of the instructions in run, including instructions in methods that run happens to call, make up the thread in the technical sense. Now, in summary, we've got three threads, main, T1, and T2. Main's job basically is to create and start T1 and T2 and wait for them to die. A thread dies. It terminates when it exits its run method. And we'll see that in the code momentarily. Now keep in mind, this is deliberately bad code. I'm trying to create a race condition, and it's not so hard to do it, as you'll see. So let me start up here. In the class race C, I've got a static member, a field called n. There's exactly one n, so that represents a single memory location when this program executes. And then I've got a method called race, and I'm going to call race repeatedly from main, and we'll see main in a bit. So here's basically what happens. Each time race gets called, n is initialized to 0. I then have a limit. It's a pretty big number. It's 4 billion or so. You see here thread T1, down below thread T2. Each of these has a run method that is executed when the thread is executing. Now the only difference between the two run methods is this. In the T1 thread, n is incremented 4 billion times or so, and in the T2 method, n is decremented 4 billion or so times. So since the value starts out as 0, and it's incremented by 1 and decremented by 1 the same number of times, the expected result should be 0. And of course, it's not going to be that because we're going to have a race condition. Let me just look ahead a little bit. I'm not going to dwell on this point right now. We'll come back and review it later. If you look at the increment, it's n equals n plus 1, and at the Java level, that's a single statement. At the executable level, however, it's really two statements. It's an increment, n plus 1, and it's an assignment, n equals that incremented result. So each of these threads executes, in effect, two instructions for each increment or decrement. All right, now back to the main code. These two lines, T1 start and T2 start the threads. Conceptually, this basically registers the threads with the Java runtime, and when the threads are assigned to a processor, the runtime is going to invoke the appropriate run method. So the run methods encapsulated in the threads are, in effect, callbacks that the system invokes. You and I, at the programming level, do not call run. Normally, we call start. I have a little try block here, and you see T1 join and T2 join. More about this a bit later. For now, it suffices to say this causes the main thread to wait until T1 and then T2 terminate. So main, you might say, is going into a wait state until T1 and T2 have done their thing. The reason is this print statement down here at the very end. The main thread, after T1 and T2 have terminated, prints out the result of n. Now, normally I would compile and then run this code at the command line. You can do that. The reason I'm not going to do it is that it is painfully slow. It's like watching paint dry because we're talking about such a big number. Each thread is doing its thing 4 billion times or so. So this is where race is called, the code we just looked at. And here's output from a sample run. So I basically have 8 lines of output. The important thing to note is that we never get 0, and we never get the same result. In other words, something is obviously terribly wrong. We have a race condition, and that race condition has led to an unpredictable result. What we need to do now is to analyze a little more carefully exactly how the race condition arises. We'll do that in the next lesson, so now is a good time to take a short pause. In this lesson, we're going to take a very close look at how a race condition occurs. The analysis should make clear what has to be done to avoid race conditions. Let me move down to the depiction and make the summary points that are listed above in the bullets. Let's assume that T1 and T2 are two threads. We're on a multiprocessor machine. T1 and T2 are executing at the same time. Each thread is accessing the memory location n. So n represents a shared memory location. T1 is trying to increment n, and T2 is trying to decrement n. So T1 is trying to execute n equals n plus 1, and T2 is trying to execute n equals n minus 1. Now, if these two statements, n equals n plus 1 and n equals n minus 1, are truly atomic, then no race condition is going to occur. In most programming languages, however, statements such as n equals n plus 1 are single statements at the source code level, but not at the compiled code level. So the corresponding machine instructions are probably 2, and it's this that's going to open the door to a race condition. In particular, n equals n plus 1 is going to break down into an increment instruction and an assignment instruction. And the same thing with n equals n minus 1, a decrement instruction followed by an assignment instruction. So what I've depicted down here to the right of the cursor is the situation for n equals n plus 1. So temp1, this might be a general purpose register, it might be a stack location, we don't care right now. Temp1 is going to hold the incremented value, n plus 1. At this point, notice n has not changed. All we've done is add 1 to the current value of n and store that in temp1. So temp1 is currently 6. Followed by n equals temp1, n's value is now changed to the new incremented value. Now, let's move down to this lower depiction, and let's walk through a scenario in which a race condition occurs. So to the left, you see C1, C2, C3, and C4. Those represent clock ticks. So we have the first tick of the clock, C1, the next tick of the clock, C2, and so on. The assumption here is that each of these instructions can be executed in one tick of the clock. And for the current example, this is not unrealistic, particularly if temp1 and temp2 are general purpose registers. But in any case, let's make that assumption. So at the first clock tick, temp1 equals 5 plus 1 or 6. So this is the increment operation that T1 carries out. At the second tick, C2, temp2 equals n minus 1. So temp2 holds the decremented value 4. So at this point, we have an incremented n and a decremented n saved in temporary storage locations. At C3, n is assigned temp2, so n's value is now 4. And at C4, we complete the increment operation with the assignment, so n is assigned the value of temp1, and it moves to 6. So at this point, in effect, n has been incremented and decremented once, so its value should remain 5, but it isn't 5, it's 6, because, as is typical with race conditions, the guy that comes in last wins. So in other words, the last assignment is the assignment of temp1 to n, and so that's the current value of n. Now, this is the root cause of race conditions. What you have, in effect, are source code statements that look atomic but are not atomic at the machine code level. So when the code gets compiled down into executable code, you have multiple instructions, and those instructions can be interleaved in inappropriate ways. To put it differently, at the machine code level, n equals n plus 1 and n equals n minus 1 are not uninterruptible. They're not atomic. The solution, I think, is pretty clear. What has to happen is this. If one thread, for example, in this case T1, starts the operation with the increment, it must be allowed to complete without interruption the corresponding assignment. So what should happen is this. At C1, you should have temp equals 5 plus 1, and then at C2, you should have n equals temp1. If that were to be the case, then things would turn out as we'd expect them to. After one increment and one decrement, n would be back to where it started. Its value would be 5. So the prevention of the race condition requires, in effect, that certain sequences of instructions be executed without interruption, as if they were atomic. Another way of putting this is that statements such as n equals n plus 1 and n equals n minus 1 must be regarded as critical section code. That is, code that must not be interrupted during execution, even if it involves multiple statements at the machine level. In the next lesson, we'll take a look at some programming constructs that enforce exactly that sort of non-interruptibility. So now is a good time to take a short pause. This lesson focuses on programming constructs for coordinating threads and thereby avoiding race conditions. Let's start out with two short code examples, the first in C and the second in Java. The working file is called thread-sync-code.java. The Java extension is there just so we get the nice color coding in the Emacs editor. So let me begin with the C example on line 1. I'm declaring a static variable. The name of the variable is lock. The static ensures that we have exactly one copy of this. So there's a single lock, and you can see the data type is called pthread mutex_t. The important word for us is mutex for mutual exclusion, and this is a very common coordination construct. In fact, it's the most basic one. So here's the function increment n, and the idea is we take the incrementing code, n equals n plus 1, and we lock that up in a mutex. So conceptually, here's the idea. Let's suppose two threads are trying to execute increment n, and they both call it at the same time. Exactly one of those threads will be able to grab the lock, that's the jargon that's used, at line 3, and the thread that grabs the lock is allowed to proceed to do the increment operation, and then the line at line 5 releases the lock. Only then could any other thread grab the lock and do the increment. In effect, then, the mutex ensures that you have single-threaded execution of n equals n plus 1, which is exactly what we want to prevent a race condition. Here's the equivalent code in Java. Once again, a static variable n, so we have a single copy of n in play, and then a static lock. It can't be null. That's one of the rules in Java. So the lock can be any non-null object reference. And here's increment n. We now use a synchronized block. So you see the keyword synchronized. The parameter is the lock, and then there's a block of code that contains n equals n plus 1. So these are comparable constructs in C and in Java to ensure single-threaded execution of a critical section of code, which thereby prevents race conditions. What I'd like to do now is take a more general look at the constructs available for thread coordination and to get some jargon out on the table. So I'm going to go to a second working file. This one is called thread-sync.txt. It introduces some of the jargon, and it represents our first look at different mechanisms for thread coordination. So let me come down to the second bullet point and review critical section. So a critical section of code for us is code that must be executed in a single-threaded fashion because otherwise a race condition could arise. And again, the standard example is n equals n plus 1. We're focusing on multi-threading, so the context is multi-threading, but in general, a critical section of code could arise in multiprocessing if there was, for example, shared memory. But we're going to focus on the threading version of this problem. Now, a good locking mechanism should have certain features, certain properties, so let's review those quickly. First, the locking mechanism should ensure mutual exclusion. In other words, if one thread grabs a lock, no other thread should be able to grab that lock, and you can't enter the critical section of code unless you hold the lock. The second property seems obvious, but it's still worth stating. The locking mechanism should ensure what's called progress. In other words, if no thread currently holds the lock, then some thread should be able to grab the lock. You might have, in effect, too much protection. So you might have a critical section of code you don't allow any thread to enter and execute that critical section. So we don't want that. That would represent overkill. Now let me talk a little bit about the locking mechanisms, because we're going to see all of these in code examples. And I'm going to start with the semaphore. And the semaphore, I'm going to move immediately to the sub-bullet, because the semaphore is often explained using a ticket metaphor. So if you think of a critical section of code as a section that allows access to a resource, we might want mutual exclusion. In other words, at most, one thread can touch that resource at any time, But we also might want something that is not quite that restrictive. So for example, we might have a resource and we would allow 3 threads at a time to access it, but not 4. So a semaphore, sometimes called a counting semaphore, is sometimes explained using the ticket metaphor. A semaphore is a ticket that grants access to a resource. You can set a value on a semaphore, so a semaphore with a value of 3 would allow, in this context, 3 threads to hit a resource, but not 4. A mutex is basically a semaphore with a value of 1. In other words, the mutex for mutual exclusion means exactly that. If one thread grabs the mutex, then no other thread is allowed to do so until the mutex is released. So a mutex, again, taking a broad view of things, is a special case of a semaphore. Java, by the way, supports both semaphores and mutexes. We'll see examples of both. Now, in the previous working file, we saw an example of a Java synchronized block. A Java synchronized block implements, in effect, a mutex, but also something beyond that. In other words, in addition to doing the excluding thing, so a synchronized block will do exactly that. It will ensure single-threaded execution of a critical section, but a synchronized block also is a mechanism for thread cooperation. So let me give a very simple example. Suppose we have 2 threads, T1 and T2, and they're supposed to execute a critical section in that order. T1 first, then T2, for whatever reason. Now, suppose that T2 hits the critical section first and manages to grab the lock. What T2 can do is put itself to sleep, in other words, go into a wait state, thereby releasing the lock so that T1 can grab it and execute. When T1 is finished, it can then awaken T2. I appreciate that that's a rather complicated scenario. I wanted to get it out. We'll look at it at the code level a bit later, but the idea is the synchronized block not only does exclusion, it also opens the door to cooperation. And so we'll see examples of that as well. Let me summarize the points made so far. The constructs that we've looked at in this working file might be described as explicit locking constructs. So the programmer uses a keyword such as pthread underscore mutex lock, something like that, or synchronized in Java. So the programmer does something explicitly to lock a section of code. There are other ways to ensure thread safety, in other words, to prevent race conditions, but we're starting with the basic way, and the basic way is to do explicit locking. In this lesson, we're going to focus on a second challenge in multi-threaded programming, deadlock. Let me go back to race conditions and give a general characterization. Race conditions arise because we have too little thread coordination. For example, we have 2 threads that are trying simultaneously to update a given memory location, and we don't coordinate their access to that memory location. Deadlock results from the opposite. That is, deadlock results from too much thread coordination. So, what you see in my Emacs editor is the source code for a file called deadlock.java. This program is contrived in that it deliberately causes a deadlock, and we'll see how in a moment when we examine the code, but let's run it to begin. So I'm going out to the bash shell, and I've already compiled the program. I'm going to run it, Java deadlock, and you see some messages on the screen. We'll get into the details of that in a moment, but you can see that I don't have the command line prompt back. My program is basically hung. So I have to do a Control-C in order to abort the program. And if I run it again, as you would guess, things are not going to get any better. The only difference you're going to see is that in the second case, it just so happens that the output is slightly different. You get a message about thread 1 first. In the prior run, you got a message about thread 2 first. So there is a little bit of variation in the program, and it's possible, although highly unlikely, that the program might not deadlock. But we're going to see that the fix is in. I do my best to make sure that it does deadlock. So let me return to the source code, and we'll walk through this rather carefully. So right at the top at line 1, I create lock1. That's the object reference, but again, for simplicity, I'm going to refer to that as the lock. In other words, as if it were the object itself. And in Java, any object can serve as a lock. The object reference must not be null. So I have lock1 and immediately below it lock2. We then move into main, and what main does is creates two threads. One is created here, thread 1, the other down here, thread 2. And you see the run methods for the two threads. So thread 1 executes the run method right above line 2, and thread 2 executes the run method right above line 7. Now the run methods have two synchronized blocks apiece. This is what causes the deadlock in this case. So let's go up to line 2. You see there's a synchronized lock 1. So basically what we have here is a mutex. Only one thread can grab this lock, and this particular run is the run that thread 1 executes, so it's going to grab the lock, and it's going to print out a message to that effect. And then this is where the fix is in. We put the thread to sleep. So basically what I'm going to do is to give thread 2 a chance to grab lock 2. Now, if you go down to line 7, you see that the run for thread 2 has a synchronized block. Lock 2 is the lock that corresponds to that block. So thread 2 is going to grab lock 2. So at this point, thread 1 is going to hold lock 1, thread 2 is going to hold lock 2. They could have grabbed those two locks in principle in either order, but the important thing is that the sleep pretty much guarantees that each thread will grab its lock. Now, let's move back up. The code is basically parallel. If you come down to line 4, the parallel code is at line 8. What's going to happen now is that when thread 1 wakes up, and after it does the print statements, it's going to try to grab lock 2. But lock 2 is already held at this point by thread 2. And here's the key idea. At the end of the synchronized block, so line 5 in this case, lock 2 would be released if thread 1 ever managed to grab that lock. And down here at line 6, lock 1 would be released automatically if thread 1 were ever able to get this far. But at present, if you visualize it, thread 1 is waiting here at this synchronized block trying to grab lock 2, which is being held by another thread. In the case of thread 2, you have an exactly parallel construction. So thread 2 grabs lock 2, then it goes to sleep, then it prints out a couple of statements. Now it tries to grab lock 1, which is currently held by thread 1. And again, the problem is that at line 9, lock 1 would be released, were thread 2 ever to get there, and lock 2 would be released at line 10, were thread 2 ever to get there, but it won't get there. These two lines, 11 and 12, basically start the threads. You could play around with this. You'll find that it's not going to matter which order you start the threads in. You're pretty much assured that deadlock is going to occur here. In other words, if this is a reasonable platform and the sleep implementation is behaving the way it should behave, 2 seconds should be enough to make sure that both threads are able to grab locks that the other threads need. Now, this example, as noted, is contrived. I'm trying to cause deadlock. The real danger, of course, is that you have a program that has a fairly complicated flow of control. You need various locks to ensure that race conditions don't occur on shared memory locations. Those locks may be nested, as the case you see here. So at line 2, I've got a synchronized block, and inside that synchronized block, I have another synchronized block. So you may have tricky flow of control, and it may be very difficult to foresee that deadlock could occur. You may do extensive testing and never have deadlock occur. And then we all know this story. We go into production, and 5 minutes later, boom, we get deadlock. Now, in general, I'd say race conditions are probably more common than deadlock, but deadlock is always something we have to keep in mind. To avoid race conditions, we need to coordinate threads. We can't over-coordinate threads for efficiency reasons, for one thing, because a critical section that is protected by a lock is basically single-threaded execution, and the whole point of having multiple threads is to have concurrent execution. So we cannot over-coordinate for efficiency reasons, but also because we may inadvertently cause deadlock. In this lesson, we're going to take a step back from the low-level details of thread coordination and also take a look forward to the sort of examples that we will see later on. So, what we're going to consider are high-level concurrency management constructs in programming languages. Over the last decade and a half, languages such as Java have put an enormous amount of effort into improving the way in which programmers attain thread safety without encountering deadlock. So Java now has much higher level data types, much better programming constructs, so that multi-threaded programming is easier to do than it was in the bad old days. That said, I'm not going to focus in this lesson on Java examples. I'm going to pick examples from a couple of other languages. We'll see those examples fleshed out a bit later, and we'll see comparable examples in Java as well. So the first example actually comes from a language that runs on the Java virtual machine, Clojure. It's a Lisp-like language. It's gotten a lot of play over the past 5 years or so. Very nice language, very high level. And it relies heavily on immutable data structures. So let me make a general point before I jump into a typical Clojure example. If you look at Java, instances of the string class are immutable. So for example, you could have an uppercase string, and there is a method called toLowercase, as you know, but toLowercase makes a copy of the original string. It doesn't change the original string, so in that sense, strings are immutable. If you try to change a string, what you're really doing is changing a copy of an existing string. So Clojure takes that approach to basically all of its data structures with very few exceptions. So let me illustrate with an example. In this little depiction, we have a thread that is accessing a list that currently has 2 nodes in it, and the thread is going to add a third node. In the basic Java approach, the list is mutable, and so to make sure that this occurs correctly in a multi-threaded environment, you'd lock access to the list while the thread is doing the update, and then the result would be this updated list. So the list is inherently mutable. In a multi-threaded environment, you need to ensure mutual exclusion when you're changing a list. Now, the Clojure approach is different, and as you'll see, there are challenges to this approach with respect to efficiency. So what we now have is the list L. We're going to add 3 to it. In Clojure, under the hood, the system is going to make a copy of that list, so I'm referring to that as LC, and it's the copy of that list that is amended, not the original list. So the list in Clojure is like the string in Java. It's an immutable type. Now let me take another example, this one from Google's language Go, which has also gotten a lot of play in recent years. And the preferred approach in Go is to have threads talk to a, you might say, master thread that controls storage. So let me explain the point this way. Go does have mutexes. In other words, they have the counterpart, in effect, of a synchronized block in Java. But they also encourage another approach. Suppose we have a multi-threaded environment. I'm depicting that down here. We have thread 1 and thread 2. We now have a third thread that I'm just calling T. And let's assume that T has sole access to the list. And the list currently has 2 nodes in it, as you can see. Now, we don't let thread 1 or thread 2 access the list directly. Instead, Go provides thread-safe channels that allow thread 1 and thread 2 to communicate with T. So the idea is thread 1, for example, might want to add 3 to this list. It communicates that request via a thread-safe channel to T. Thread 2 wants to add 33 to the same list. It communicates that request through the same thread-safe channel to T. T is now responsible for correctly serializing those requests. In other words, adding one and then adding the other. So the thread safety is achieved, in effect, by having single-threaded access to the list, and that access is basically, if you want to call it this, the owner of the list. It's an informal notion, but it's a programming idiom that's encouraged in Go. Now, we're going to see examples like this, and we're going to see some of these examples in Java, since Java has done a lot of excellent work in improving thread-safe programming. But I thought that after looking at sort of the grimy side of multi-threading, the problems with race conditions, the problem with deadlock, it's not a bad idea to keep our eyes on the future when we're going to see higher level constructs for achieving thread safety. This lesson is a wrap-up of the multi-threading basics that we've just covered, and it also introduces some important new terms. Let's start with the wrap-up. The working document, by the way, is wrap-up5.txt. So, on the upside, multi-threading can be a highly efficient way to do concurrent programming because thread-level context switches are very, very cheap. The cost is not quite zero, but it comes close to that. In languages such as Java and C#, there's no question but that multi-threading is the preferred way to do concurrent programming. You can do multiprocessing in those languages. Both languages support non-blocking I/O, but multi-threading has a special place in both languages. Now, multi-threading does come with its challenges, in particular for the programmer, and we've seen those, and we'll see more examples of those in a bit. So one challenge is that the programmer needs to avoid race conditions to make sure that multiple threads don't access shared memory locations in bad ways. Put in more formal terms, what the programmer has to do is to ensure that critical sections of code are executed in single-threaded mode. One way of doing that, and the way we've emphasized so far, is to use a mutex. In Java, for example, that's a simple synchronized block. Now, avoiding race conditions is one challenge. The twin challenge is to avoid over-synchronization. In other words, not to overuse mutexes, because what that does is to degrade performance. After all of the code executing within a mutex is executing in single-threaded fashion, and so you're losing the efficiency that can come with multi-threading on a multiprocessor machine. So over-synchronization can degrade performance, and in the worst case, it can lead to deadlock. What we haven't seen in detail, but we'll begin to see in examples now, are higher-level constructs for thread coordination. So languages have done a lot of good things in the last decade and a half or so in order to make it easier for programmers to coordinate threads. And we'll be looking at that very closely. So there's some light at the end of the tunnel. The point that I'd like to close on, though, is this. Even with the new higher-level constructs for doing multi-threading, sometimes the simplest, the most obvious, the most natural way to go is with a mutex. In other words, to have a lock, a short block of code, and then to release the lock. And we'll have occasion to see that again in forthcoming examples. Let me turn now to some important jargon. In particular, I'd like to clarify green threads and talk a little about what's known as the Global Interpreter Lock, almost always abbreviated as the GIL. Here's the basic idea. A native thread, and this is a phrase you'll run into a lot in the multi-threading literature, a native thread is a thread that's under direct operating system control. So the operating system kernel schedules the thread, preempts the thread, and does all of the bookkeeping required to manage the thread. In Java, since roughly 2000, so that would be about JDK 1.4, Java thread instances, so instances of that class map to native threads, and C# threads also map to native threads. In C, pthreads, and pthread is actually a standardization API from POSIX, but pthreads are likewise native threads. A green thread is in contrast to a native thread. And a green thread is sometimes called a microthread. You'll hear the term tasklet used occasionally. And the idea is that a green thread emulates a native thread, but a green thread is really under a particular language's runtime control. So in Ruby 1.8 and earlier, for example, Ruby threads are green threads, they're not native threads. Starting with Ruby 1.9, Ruby threads are green threads. Now, an independent issue is whether a language has a so-called GIL, Global Interpreter Lock, and this is a mechanism that a language uses to ensure that only one thread executes at a time. This has to do with the internals of the language's runtime. We don't need to get into those details, but the problem with a GIL is this. With a GIL, you can have concurrency, but you cannot have true parallelism in an application. That's because even if you have multiple threads at the application level, only one of those threads is going to execute at any given time. The standard implementations of Ruby and Python, those would be C Ruby and C Python respectively, both have a GIL. This wrap-up should be useful as we move forward to the next topics. This lesson recommends a short programming exercise on the basics of multithreading. In particular, the idea is to fix the race C program. The race C program has a race condition. There are critical sections of code that are not protected with a mutex, which causes the race condition. Now, we've seen the code required to do the fix. I still think the exercise is worth walking through because as you think out how to do it and actually then implement the synchronization, you learn a lot. I've always found this to be the case for me, and I hope it works the same for you. So let me go back to the race C program briefly and talk about a couple of things and recommend how you proceed. So the first thing is this. I set the limit very, very high in the original program. The limit is the number of times that the two threads do their thing. So thread T1 increments n, shown above here, and thread T2 decrements n, and each of those threads does this a limit number of times. I've set limit to over 4 billion. You may want to reduce this sum in order to make the program run faster. I'd still recommend, however, that you keep the value somewhere in the million range. Now, T1, this thread, its critical section is the code n equals n plus 1, the incrementing code. And for thread T2, the critical section code is this code, n equals n minus 1. So those are the chunks of code that need to be protected, that need to be synchronized to ensure that there is single-threaded access. To do this, you need a lock. My recommendation is you create a static object reference. You need to initialize it. It can't be null. Because if you have a static object reference pointing to an object, then you're guaranteed to have a single object. There's no confusion. There's no need to think it through too carefully. There are other ways to provide a lock, but to begin, this is certainly the easiest way, and it's also a production level way of doing so. Let me now return to the working file, exercise mt.txt, and let me suggest a second aspect of this exercise. One of the things that's going to become clear, even when you run the code from the command line, is that the synchronized version, the fixed version, is going to be noticeably slower than the original version. So there's obviously a cost to thread coordination. In particular, you're going from multi-threaded execution on a multiple processor machine to single-threaded execution. So things are going to slow down. There's bookkeeping that needs to be done and so forth. There's just built-in overhead. So it would be nice to quantify that difference. So what I recommend is timing. Time the original and then time the fixed version. There are many ways to do this. You may be doing this regularly in your everyday job, and so you could use those techniques. But within a Java program, a relatively simple way to do it is sketched here. So in the system class, there's a static method called current time millis. You get the current time in milliseconds. You can then, of course, compute the stop time and then the latency, the response time, is simply the difference between the two. I think you'll find that the results of this will confirm the intuition that there's a cost to synchronization. This lesson introduces a series of related examples. This series is meant to take a systematic look at 3 questions. So the first question is this: how do threads behave? In other words, if we don't coordinate them in any way, what's their basic behavior? And we want to see that, of course, at the code level. The second question is, what are the different ways for us to coordinate threads so that they behave appropriately? There are many answers to that second question. There are different ways to coordinate threads. Some require more work on the part of the programmer than do others. And we'll begin to take a look at both the low-level or basic ways to coordinate threads and the higher-level ways. And the third question is, how can we make threads cooperate with one another so that we boost program performance? In other words, we'd like to use thread cooperation as a means to achieve program efficiency. The first example is in C. We want to look very closely at what the system does, so we want to be as close to the metal as possible. And I'm going to pick a standard sort of example, and I've depicted it here. This is the working file Miser-Spendthrift.c. The very top line shows how it can be compiled, and I'm going to execute it in a bit. So let me begin with this simple depiction. We have a bank account. It's shared between 2 threads. The Miser thread wants to increment the account, and the Spendthrift thread wants to decrement the account. In order to keep things simple, in this first example, the increments are always by 1. So the account starts out as 0, the Miser adds 1 to the account, and the Spendthrift decrements the account's balance by 1. The increments and decrements are going to occur, as you'd expect, the same number of times. So when we're done, we should wind up with 0 as the account's balance. The number of times to increment and to decrement is given as a command line argument. Now let me walk through the main features of the code. We're not going to dwell on each and every syntax aspect. We don't care about that so much. It's the overall concurrency that we're interested in. So to begin, you see I've got a static integer variable named balance. It's initialized to 0 for emphasis. The compiler would do that in any case. The keyword static ensures that we have exactly 1 copy of this. So there's a single balance memory location, and it has 0 to begin. Report and die is just a utility function. If something goes terribly wrong, an error message is going to be printed, and the program's going to exit. Now, these 2 functions are very important: deposit and withdraw. So let me just say a word about each of these. You see a very peculiar data type in C, if you're not familiar with the language. Void star, which is read pointer to star. Void star in C is the counterpart, roughly the equivalent of a type such as object in Java or C#. So it's a very broad, embracing data type. Basically, anything with enough effort can be converted to void star in C. So the idea is this: deposit and withdraw are the 2 functions that our 2 threads are going to execute. So these are the execution sequences that actually make up the thread. The single argument, in this case n, allows us to pass information to deposit and later to withdraw. And n is going to be the number of times to iterate, basically. We also get a chance to return a value from deposit and withdraw. In this particular example, there's no need to do so, so I'm returning 0, which is the same thing as null in C. The important thing is this: if you come down to line 3 in deposit, and the counterpart is line 5 in withdrawal, you see what the application logic is. So the Miser thread is going to increment the balance by 1. That's the balance plus plus. And the Spendthrift thread is going to decrement the balance by 1. That's the balance minus minus. So in effect, these are going to be the callback functions for the threads. In other words, we're going to ask the system to create and start a thread, and we're going to specify deposit and withdrawal as the two functions that the two threads should execute. So let me now come down to the main function at line 6. This top part is not so interesting to us. Basically, we're going to read in a command line argument. I'm going to use a fairly big number, 50 million, when I run this. So that's read in as a string, converted to an integer, and that integer is n. Now we get into the pthread API. So at this line, 7, we declare two variables of type pthread_t, Miser and Spendthrift, so those represent our threads. The call to pthread create takes 4 arguments. For the first call, I've put those on separate lines for clarification. So the first argument is the address of the Miser variable. The second argument would allow us to specify some attributes. For now, we're going to take the defaults, and so that argument is set to 0 or null. The third argument is the really important one for us. It specifies the function that the thread should execute when it started, and that's the deposit function that we saw earlier. And the fourth argument is the address of the number of times to iterate, and that variable is the n that you see up here. That's the conversion of the command line argument. If pthread create returns -1, so in other words less than 0, there was a problem in creating the thread. Maybe the system has too many threads. Maybe we don't have the right privileges to create threads. I call report and die, which prints out an error message and terminates. That shouldn't happen, at least not in this simple example. This is the other call to pthread create. So first, the Miser is created, then the Spendthrift. You could play around with this, but you'd find that the order in which you create and start these threads is not going to matter. You're going to get essentially the same behavior. Lines 11 and 12 are important for this reason. The main thread, which creates the other two threads, is also responsible for printing out a report down here at line 13. And the main thread is going to report on the final balance. Obviously, we don't want this to happen too early. The other two threads, the Miser and the Spendthrift, should have died before main prints out its report. So the pthread join accomplishes exactly that. The main thread waits here at line 11 for the Miser thread to complete its work. The Miser thread will have completed its work when it exits the deposit method. Down here, the Spendthrift thread will have completed its work when it exits the withdrawal method. So once that happens, control returns to the main thread, which then proceeds down here to the print statement and prints the final balance. There's no thread coordination in this example, so the threads are, so to speak, out there in the wild, doing whatever they want to do. So let's run the program and get a sense of what it is that they do. So I'm going to go to my bash shell, and I've already compiled the program. I'm going to run it. That command line argument is 50 million, so I've deliberately picked a big number. And you can see that I get a non-zero result. I'm going to do it again. Another non-zero result. Another one. This happens to be non-negative. Yet another one, negative, and so on. The thing to notice, of course, is that we don't get 0 as the result, even though the same number of increments and decrements occurs. We don't even get the same number twice. Some of the numbers are relatively close, but there's really no noticeable pattern in the short number of tries that we've given here. Over time, the expectation would be that we'd get roughly the same number of negative as non-negative results, but other than that, these answers look as if they were random. And this, of course, is because we have a race condition, and we have a race condition because we have uncoordinated threads. So what we're going to do in the next lesson is fix that. In this lesson, we're going to fix the example shown in the previous lesson. That is, we're going to make sure that the Miser-Spendthrift program works correctly. So the working file you're looking at this time is Miser-Spendthrift fix.c. And before we examine the source code, I'd like to move to the command line prompt and run the old version and the new version. So here's the original program, Miser-Spendthrift. I've picked a much smaller command line argument, 500,000 instead of 50 million, for reasons I'll get into shortly. But let me just run this a couple of times. So we get a non-negative value, another negative value, yet another, one more non-negative value. So let me clear the screen. Notice, by the way, that the program ran very fast with those numbers. So let me now do the fixed version. So I'm going to pick fix here, run it with the same number. Notice there's a noticeable pause. Let me do it again. Pause. We'll do it a third time. Make sure it's a charm. But of course, we get the right answer every time because the threads are now coordinated in order to prevent a race condition. So let's go back to the source code and look at what's changed. Line 1 is the same as before. There's a static variable called balance that represents the balance of the bank account. It's initialized again to 0 for emphasis. The change now is this. We have a data type called a pthread mutex key. That's going to be our lock. I've made this static again for emphasis. I want to make sure that we have exactly one lock, that we're using the same lock. There are other ways to make sure we have a single lock, but this is the most obvious one. Report and die is the same as before. It's just a little utility method. And the two methods of interest, let me situate the cursor a little better here, are deposit and withdrawal once again. So those haven't changed. In each case, we're going to pass in as n the number of times that each of these threads should do its thing. So the miser and the spendthrift are going to do their relative tasks exactly the same number of times. And that's going to occur in a counted loop, in this case, C's for loop. The difference now is the following. In the original version, there was no locking of the increment and decrement operations, but this time there is. So at line 3, using pthread mutex lock, quite a mouthful, and passing the address of the lock, we check to make sure that the lock took. If there were a problem, we'd get back -1. So in this case, if the lock succeeds, we're now guaranteed that incrementing the balance, this critical section of code, is done in single-threaded manner. In other words, the balance is not being decremented at the same time. It's being incremented only. Once the increment and assignment operation is completed, so in other words, balance plus plus is really balance equals balance plus 1, we release the lock, and in this case, there's nothing to return, so I just return 0. The withdrawal function is essentially the same. The locking is exactly parallel to what we've just seen. The only difference is that the critical section code is now the decrement operation, balance minus minus as opposed to balance plus plus. But otherwise, these are exactly the same. There are some small changes to main, so let's look at that. The changes mostly have to do with setting things up and then doing some cleanup at the end. So once again, we prompt for a value from the command line, convert that into an integer. So far, the same. We've got two thread variables, miser and spendthrift. Those are the same. This is different. Line 6, right below it, pthread mutex init. So this initializes the lock. So this is a call to a very important library function. If this line is not present, the code would still compile and run, but you wouldn't get proper locking. In other words, it would be as if you had the original code. The race condition would still exist. So the init is very important. After doing the init, we create the two threads. That code is the same as before. The main thread then waits for the miser and the spendthrift to complete their work, exactly the same as before. But then for cleanup, we call destroy on the lock. Basically, we're telling the system the resources that you needed to create that lock, you can now recover those resources. We don't need those anymore. So in a production-grade program, you'd certainly want to put this in for efficiency reasons. In this case, it doesn't really matter, but it's good practice to have that in. And then finally, the balance is printed out. The most noticeable thing about this improvement to the program is the cost of synchronization. In other words, the thread coordination comes at a performance cost. The unfixed version runs very fast, but of course gives us all of these arbitrary answers. The fixed version always returns 0, but it does so more slowly. So the cost of thread synchronization is non-trivial, and that's a theme that we'll see over and over again. This lesson presents an overview of the 3 examples to follow. Each example is in Java, and each example has the same 2 files in it. So let me explain the layout. I've put all of the code together in a zip file. The name of that file is down here at the first bullet, Miser-Spendthrift Java.zip. That's included in the working files. We're looking at Miser-Spendthrift Java Overview.txt, the text file that basically gives the layout. So for convenience, all of the code is packed into a single zip, and here's the directory structure. There, as you can see at the top, a directory called code, and underneath it, 3 subdirectories, account, account2, and account3. Those, of course, serve as Java packages, and then each one of those has 2 source files, account.java and racecondition.java. There are different implementations at the account.java level. The race condition code is essentially the same, except for the package differences, and the racecondition.java source files contain main. So basically, that's where the application is run from. Now, if you come down here, this basically explains the differences among the 3. In the first implementation, with package ACCT, there's a deliberate race condition, just as we saw in the C example. ACC2 fixes that race condition by using explicit low-level synchronization. So in Java terms, it uses synchronized blocks. And finally, ACCT3 uses a high-level fix. It basically introduces the atomic integer data type, and the atomic integer bakes the synchronization into its own methods, so there's no explicit synchronization. You'll see, I think, that the third implementation is far friendlier than the second one, although the second one is reasonably straightforward. Now, in this first bullet point, this is basically the structure of the zip file, so I've included the source code, but I've not included the compiled. I've not included an Ant or a Maven script because this code is so straightforward. Instead, if you'd like to work from the command line, here are the compile and run examples for each of the 3. So you'd be doing these in the code directory. You could, of course, just open these programs in your favorite IDE, compile and run from there. So that's the overview. What I'd like to do now is a quick demo. So let me bring up my command line prompt, my bash shell. I've already compiled the files, so I'm ready to run the first of these, and I'm going to run this with a command line argument of 2 million. So 2 million is the number of times that the miser is going to increment the account's balance, and the same number of times that the spendthrift is going to decrement the account balance. So we expect not to get 0 as an answer, and we'll do it a few times just for demo. So we have one positive, one negative, another positive, yet another positive, another negative. And as expected, we can see there's a race condition. We're not getting 0, and we're not getting the same value every time. Let me clear the screen and run the same thing with the second version. This version again uses explicit low-level synchronization, the synchronized block in particular. It's a bit slower, but we're going to get 0 basically every time. The synchronization is going to ensure that, and of course you could up the number a bit. Let's see how much longer this takes. We'll go to 20 million. Well, there's a significant difference you can see in the performance, but we wind up with the same answer. Let me now do the third version, which is the friendliest and is reasonably straightforward to write and to run. And as you can see, we get 0 in each case. So, to repeat, this text file included in the working files is an overview of the examples that follow. What I'm going to do when I present the examples is use a single Java file in my Emacs editor just for convenience, because as you can see here, each implementation has two .java files, and I don't want to be jumping back and forth between the two. But the executable code is in the zip, and we'll be looking at the two files in each application together. In this lesson, we're going to look at three versions of the Miser-Spendthrift problem, all in Java. The first version deliberately induces a race condition, and then the next two versions fix it. You're looking at the working file Miser-Spendthrift1.java. I've put all of the source code into a single file for convenience, but remember that the zip file contains the code that should be compiled and run. So let's go over this fairly briefly because we've seen this sort of thing before. I've got a public class account which has a single static field, balance, initialized to 0 for emphasis. So since there's only one balance, we can be sure that there's going to be contention for it between the threads. And the problem is that that contention is not going to be coordinated. I've got two classes, one to represent the miser, the other to represent the spendthrift. So those are lines 2 and 3 respectively. Each of them extends the thread class and overrides the run method. What you're seeing here is an example of the so-called adapter pattern. In the thread class, the run method is defined, but with an empty body, so it doesn't do anything. In a subclass such as miser, what we do is override run to do whatever work is appropriate, and in this case, all that we're going to do is increment the account balance by 1. The spendthrift then is pretty much parallel code, except that the account balance is going to be decremented by 1. The race condition class shown here is the same in all three examples. So I'm going to show it here, but not show it again in the other two. So the source code is exactly the same. Basically, the idea is this. Main reads in a command line argument, converts it to an integer. That integer n represents the number of times that each thread is going to do its thing. So the miser is going to increment n times, and the spendthrift is going to decrement n times. We start the miser down at line 7. We start the spendthrift down at line 8. You could reverse the order, won't make any difference. Then we have the main thread again wait for the miser and wait for the spendthrift, because the main thread is going to print out the balance at the end, and this is going to be, in effect, an arbitrary integer value. It would be a minor miracle if this turned out to be 0 if the command line argument were big enough. So I'd suggest 500,000 or greater as a command line argument. Depends on how fast your system is, that sort of thing. In any case, this code, as we saw in the last lesson, induces a race condition. Now let's look at the fixes. The first fix is shown here in the working file Miser-Spendthrift2.java, and the significant differences are these. At line 2, we add a lock. So again, just to be sure, I'm making this static. That ensures that we have exactly one lock. There are other ways we could do this, but this is an emphatic way of doing it. And I put that lock inside the account class. Why not? That's where the balance occurs at line 1. Again, initialized to 0 for emphasis. The miser and the spendthrift are essentially the same except for lines 4 and 7. So, inside the for loop at line 4, we have a synchronized block using the lock encapsulated in the account class. So this statement here at line 5, incrementing the balance, is guaranteed to be single-threaded execution. And this line here, down at line 8, is likewise guaranteed to be single-threaded execution because we're synchronizing on exactly the same lock. So in effect, the synchronized block in both cases acts as a mutex. It ensures mutual exclusion only one thread at a time gets to execute its business logic, if you like. Now, the synchronization in this example is pretty straightforward. The critical section code consists at the source code level of a single statement, line 5 in one case, line 8 in the other case. So this is not overly complicated. This is a perfectly reasonable solution to the problem. But what I'd like to do now is to look ahead a bit and to show you the sort of thing that Java has added for concurrency management. So let me bring up a third file, and that's Miser-Spendthrift3.java. And the significant difference now begins at line 1. You can see there's an import, java util.concurrent. That package and its subpackages contain, in effect, all of the new constructs that Java has added over the years to make thread management easier. So it's really very, very nice stuff. And in this case, I'm using, under java util.concurrent, the atomic subpackage, and in particular, the atomic integer. And you'll see why it's called that in just a moment. Most modern languages, by the way, have a counterpart for that. So the balance is now implemented as an atomic integer instance. Basically, it's set to 0 at line 2. And we now have the miser and spendthrift threads yet again. But the difference is this. Notice that in the run methods, there's no explicit synchronization at all. And that's because the synchronization is actually baked into the atomic integer class. So at line 3, we call the method increment and get, does exactly what you'd expect. It increments the balance and then returns the value. We don't use the return value here to do anything. We care about the side effect, the incrementing. And down here at line 4, you have the account balance decrement and get. There's no explicit synchronization. There's no need for explicit synchronization because the synchronization is actually built into the methods increment and get and decrement and get. So this is a very nice solution for this problem. And in fact, for this particular problem, the Miser-Spendthrift problem, this is an ideal solution because there's very little clutter. There's no danger of our making a mistake with the synchronized block, that sort of thing. It really is pain-free thread coordination. In this lesson, the focus is on thread cooperation rather than on thread coordination. Let me clarify with a note from history. Java's synchronized block is meant to implement what operating systems people call a monitor. And that's a programming mechanism that supports, for example, mutual exclusion in order to coordinate threads. So we've seen that, the use of mutual exclusion to avoid race conditions. But a monitor likewise is meant to foster thread cooperation. And the motivation here is efficiency. For example, imagine that you've got multiple threads contending for a lock. We know that only one thread can grab that lock at a time, and the question is, what are the other contenders going to do in the meanwhile? Well, if they keep contending, so if you think of them as executing in a very tight loop, trying to grab a lock that another thread has, this is a waste of resources. The most obvious resource being wasted, of course, is a processor. So the question is, can we do better than that? Can we come up with other mechanisms that allow threads to cooperate rather than simply to contend? So to illustrate this point, I'm going to take a classic programming pattern, the producer-consumer pattern, and illustrate it as depicted here in my Emacs editor. So the working file is syncascooperate.txt. So I've got a very simple illustration. There's a queue, as you can see, with 6 items. This could be implemented, obviously, as a simple array. And just to fill something in, I've got integer values, arbitrary values, sitting in the queue. The important thing is this. We're going to have multiple producer threads. Those are depicted on the left, which can do insertions into the queue, and multiple consumer threads that can do removals, and those are depicted on the right of the queue. And of course, to pull this off, we need 2 special indexes into the queue. Back and front, of course, are the familiar terms used to describe these. On every insertion, the back has to be adjusted, and on every removal, the front has to be adjusted. So there's some bookkeeping. Now, the need for mutual exclusion is intuitive, I think. You can't, for example, have two producing threads simultaneously try to insert something into the queue. You can't have two consuming threads simultaneously trying to remove something. And of course, you can't have a producer and a consumer simultaneously accessing the queue either, because you need to keep those indexes in proper order. So what I'd like to do is focus on the cooperative side of this now by considering two cases. I've described the cases below, but I'm going to keep the cursor here in order to use this as the illustrative point. So consider a situation such as the following. Suppose that the queue is already full. So that's depicted right now in this situation. So we've got 6 at the back and 7 at the front, and everything in between is filled as well. So because we have a fixed size queue, nothing else can be inserted. Now, a producing thread tries to insert something, and the question is, what should it do? Well, the application logic is going to prevent the insertion, of course, because the queue is currently full. So there are two possibilities. One is that the producer could sit in this tight loop described earlier and simply try repeatedly to insert. It might, for example, put itself to sleep, sleep for 10 milliseconds, wake up, try again, that sort of thing. That would be a slight improvement, but there's another possibility. A producer who can't insert because the queue is full might simply put itself to sleep indefinitely, and then when a consumer removes something from the queue, the consumer, as part of its application logic, could then awaken any sleeping producers. The idea then is that the producer would go into a quiet state, not use up any system resources when it detects a full queue, and a consumer, by removing something, renders the queue no longer full, and so can awaken producers and basically give them the opportunity to go back to producing. On the other side, a consumer cannot consume from an empty queue. So again, you can imagine a scenario where a consumer goes into a tight loop and repeatedly checks to see whether something has been inserted into the queue. And again, you could have some different approaches, slight variations. The consumer might put itself to sleep for a little while, check again, go back to sleep, check again. But following the same pattern as before, what we might do is this. If a consumer detects an empty queue, the consumer puts itself into a quiet state, in other words, a wait state, indefinitely, and a producer, when it inserts something into the queue, awakens any waiting consumers. So you've got here a scenario that boosts the efficiency, but doesn't interfere with the underlying application logic. Producers still insert things into the queue, consumers still remove things from the queue. So what I'd like to do in the next lesson is introduce a programming example that shows cooperation. I'm going to make one slight adjustment. Instead of using a queue, I'm going to use a stack. And conceptually, the difference between a stack and a queue is this. In a queue, you have two places of interest, the front and the back. So the back is where the insertions occur, the front is where the removals occur. In a stack, the insertions and removals occur at the same end, traditionally known as the top. So I've illustrated a very simple stack here with 7 at the top, 3 below it, 9 below it, and so forth. So once again, at the implementation level, we're talking about an array or a list of some sort. The bookkeeping is slightly simpler, so I think the stack will be more useful because we can focus not on the bookkeeping, but on the thread cooperation. In this lesson, we're going to look at the producer-consumer program in Java. The program is called stackts. You see the source code in my Emacs editor, stackts.java. And above the cursor, there are instructions for compiling and then running the program. So this program is going to give equal weight to thread coordination in order to avoid race conditions, but also thread cooperation in the interest of efficiency. So let me get to the main class, which is stack TS, the TS for thread safe. The stack in this example is going to have a capacity of 8. Our emphasis again is on the coordination part of things, not so much on the application logic. In terms of the implementation, whenever the top, which indicates the point in the stack at which insertions and removals occur, whenever that is less than 0, in particular -1, that means that the stack is empty. And here you can see the stack, just a simple Java array that takes integer values. Now, let me move down to something that we've not looked at before. So you see there's a push method here that does insertions, and down below there is a pop method that does removals. By the way, pop returns void. In real life, we would return, of course, an integer, but I'm not so much interested in the application logic, so I've simplified things. The point of interest for us is that the entire method is synchronized in both cases. So at line 1 and line 7, you see the synchronized block encompasses the entire body of the method. This is a little bit tricky at the API level because there's no obvious lock. So a synchronized block always has a lock, and the obvious question is, where is the lock? Well, in this case, when you synchronize a method, the implicit lock is the current object. In other words, this, an instance of the stack TS class. The upshot is the following. By synchronizing both push and pop, what we're saying in effect is this. One thread can call push or pop, but you can't have two threads executing push at the same time. You can't have two threads executing pop at the same time, and you can't have one thread executing push and another executing pop at the same time. So it's a little bit tricky, but it's the behavior that we want. We can't allow, for example, simultaneous pushes. I think that's clear. Or simultaneous pops, but we also can't allow a push and a pop to occur at the same time on the same stack. Now, let me look at the pop method down at line 7 to talk about the internal logic, because this again is a bit tricky in Java. So the idea is this. Suppose we have a number of threads contending to do a pop. One of them manages to grab the lock and enters the body of pop and hits line 8. And you can see here this is a while construct, not an if construct. That's a very important point. So the condition in the while construct is top less than 0. This means, again, that the stack is currently empty. There's nothing to be popped. So in this case, the thread goes into an indefinite wait. So this is the quiet state. The thread is not using any significant resources. It's going to stay in the wait state indefinitely, that is, until some other thread awakens it. There are different variations of wait. So for example, you could say wait 10, and that would mean wait for 10 milliseconds, then wake up, go back to sleep if you shouldn't proceed, and so on. Now let me get back to the while part of this, which is the tricky part. When the thread goes to sleep into the wait state, it could be awoken for any number of reasons, and the concern we have to have is that someplace else in our application logic, we might inadvertently wake up this thread, even though we shouldn't. So the idea is, even if the thread is awoken, it's going to test once again to see if the stack is empty, and if it is empty, it's going to go back to sleep. In other words, the while construct makes this wait robust. The thread might be awoken by reasons we don't foresee, but nothing is going to happen so long as the stack is empty. Now, once the stack is no longer empty and the thread has been awoken, we'll see how momentarily, we print out a little message to the screen basically saying a pop has occurred, the top is adjusted appropriately, and this is the key call of interest to us at line 12, notify all. So the popping thread now notifies any other threads that happen to be waiting on the same lock. Notice that the notify all is the last thing called inside the synchronized block, and that's what we want. So in effect, what we do is wait until the stack is no longer empty, pop something from the stack, and then as a courtesy, awaken any other threads that happen to be waiting for the lock. You find essentially the same logic up here in push. The only thing that differs is the condition. You can't push onto a full stack, so basically a thread that wants to push and which happens to have the lock is going to wait indefinitely until it's awoken. Once it's awoken, it's going to push something onto the stack, it's going to adjust the top, and then again awaken any other threads that happen to be waiting. Now, it's pretty clear, even from this summary explanation, that this is tricky business. This is yet another reason why we want to try to move later to a higher level, to higher ways of synchronizing threads, both in the coordinating and in the cooperating sense. Now, the rest of the program is not quite so tricky. I've got a pusher class, which is a subclass of thread, and as you'd expect, I override run. I go into an infinite loop, so this program has to be killed at the command line. A pusher is going to try to push indefinitely. A popper is going to try to pop indefinitely. And basically what a pushing thread does is pushes a random integer onto the stack, and then to get some randomness into the program itself, we put the thread to sleep for a bit. A popper performs the inverse operation. In other words, in its run, it just does a pop operation, and then it too goes to sleep randomly, but not for quite as long. So I want to have some random behavior in the overall program. Finally, here's the main class. And as you can see, what I've done is created a stack at line 16, and I don't want to have the same number of pushers and poppers. I'd like to adjust this a little bit, again, to try to make this a bit more realistic. So in this example, I have a single popper and a pair of pushers. I start the popper first, so this ensures that the first time the popper tries to pop something, the stack is going to be empty, so the popper has to go to sleep, has to go into the wait state until one of these two threads manages to complete a push, then there's something to pop. Let's run this program from the command line just to give you a sense of how it works. So I've compiled it already, and I'm in my bash shell. Again, main TS is the class that encapsulates main. So I run it, and now you see the screen is filled with pushes and pops. I'm just going to kill this at the command line. So for example, if you look in roughly the middle of the screen, you're going to see that there's a bunch of pops. So 69 is popped at position 7, 16 is popped at position 6, and then you see a push, a pop, a push, a couple of pops, some pushes, and so on. So if you inspect the output, you'll see that the behavior is correct. The stack is indeed thread safe. There's no race condition. There's no deadlock. It behaves as we'd like, and it does so in an efficient way because threads that want to do something but can't go into this quiet state, the wait state. In this lesson, we're going to take a look at the Multithreading Web Server. This is the second of the 3 sample web servers. We've already seen the forking server. That was the Multiprocessing Web Server. So in this example, the web server is going to manage concurrency by using multithreading instead of multiprocessing. All of the source code, together with a makefile for compilation, is available in the zip with the 3 servers. In my Emacs editor now, you're seeing a cut-down version, threading_server.c. I've excluded the includes in order to focus on the main code. So right now, the cursor is in the main function, next to the call to create server socket. So just to remind you, that's one of the functions in utils.c. Those are functions that are shared among the 3 web servers. The argument of false means this is not to be non-blocking. In other words, we're getting a blocking socket, a socket that's going to block until somebody tries to connect. The logic in this web server is very similar to the logic in the previous one. So we go into an infinite loop, while true, and basically await client connections. So this is the blocking call to accept. When a client does connect successfully, the variable client is actually a file descriptor, And as a reminder, that file descriptor describes a socket suited for reading and writing. In other words, the web server is going to use that socket to read the client request and to send a client response. So it's the usual song and dance. We check to see if we got the file descriptor. Otherwise, we generate an error message. If everything's okay, we log a message about the client connection. And now comes the concurrency. So here's a variable of type pthread_t. Again, the pthread library is a uniform API for thread management in C and C++, basically. So it's available across platforms, and it's become the de facto standard. There are other libraries, but this is probably still the most widely used one. We pass that variable, I call it TID for thread ID, to the pthread create method. So the first argument is going to be the ID, effectively, of the thread. The second argument would allow us to specify various attributes. I'm going to take the defaults. The third argument, again, is the most important one. This is the thread routine. So this is the code, a function that the thread is going to execute. And the last argument is the address of that file descriptor. We need to pass that file descriptor to the handle client function so that the handle client function can communicate with the connecting client. In other words, this is what allows us to do read and write operations with the client. So once that's done, this is a standard division of labor pattern, separation of concerns, if you like. The main thread goes back up here and starts waiting for more connections. So the division of labor is this. The main thread calls accept. When a client connects, the main thread creates a thread, hands over to that thread the responsibility for handling the client, and the main thread goes back to listening for new clients. So let's go and take a look at the handle client function, since that's basically the equivalent in Java of the run method. Now, at line 2, this is a new call. We haven't seen this. pthread detach, and the argument you can see is pthread self. So pthread self returns the ID of the current thread. So whatever thread happens to be executing this code. Pthread detach means at a high level that no other thread is waiting for this thread. So basically what we're telling the system is, as soon as the thread exits handle client, nobody is waiting for it, you can basically take back all of the resources allocated to the thread. In this particular case, this represents an inefficiency since we're creating a new thread for every client request, and that thread terminates as soon as it handles the request. As you might guess, there's room here for a nice exercise. This next line, line 3, is a bit low level, but basically what we're doing is getting the file descriptor as an int rather than as a pointer to an int. So it's low level C. We don't have to worry about that so much. Down here, the receive method reads the client request, and down here, generate echo response generates a trivial response to send back to the client, and then the call to the send function is used to send that response back to the client. At this point, we close the file descriptor, so effectively, the connection between the web server and the client is now closed. We don't, in this case, return anything, so I'm returning null or 0, and we're basically done. Now, I'd like to make one other point about handle client, and I'll come back to this point when we do the wrap-up. So the point is this. Handle client takes one argument, and everything else is either a parameter or a local variable. So the client pointer is the parameter. We've got a local variable client, a local variable buffer, a local variable bytes read, and so on. So this particular thread relies only on parameters and local variables. In that sense, handle client is what's sometimes described as a pure function. It doesn't rely on any global information. It basically has everything contained in and of itself. The key point for us is that in a multi-threading environment, all local variables and parameters are thread safe automatically. We don't have to worry about synchronization and so forth because every thread at the system level gets its own stack, in other words, its own area of memory on which to store scratchpad variables, parameters, and locals. So that's a wrap-up of the threading server. The division of labor is reminiscent of the forking server. The big difference is that the forking server uses processes to handle client requests, whereas the threading server uses threads. So what you have in the case of a threading server is an increase in efficiency, and because of the simplicity of the code, there's really no issue of thread coordination. This lesson is a wrap-up of the most recent code examples. It's time to take a step back and to look at the big picture. And the recent examples have moved from thread coordination to thread cooperation. But there still was some coordination as well. So let's start with that and then move on to the cooperation. So as we've seen from the examples, thread coordination has a wide range, even in the examples that we've seen. There are explicit mutexes. We've seen that in C, and in effect in Java with the simple synchronized block. But in the case of Java, we also saw an example of a data type, the atomic integer, that has the synchronization built in. So we just use the atomic integer in a Miser-Spendthrift example, and we could dispense with the explicit synchronization. Very nice for programming. What we're going to do in the forthcoming examples is move on to richer data structures, in particular thread-safe lists and maps. Java actually has had these from the get-go. The vector and hash table are thread-safe, but they're not efficient. Their preferred replacements are things such as the copy-on-write array list and the concurrent hash map. And those are two data types that we'll look at a bit later. They're both thread-safe and highly efficient. Now, as noted in the examples, thread synchronization in the broad sense involves not just coordinating threads to avoid race conditions and to prevent deadlock, it also means having threads cooperate so that we can boost performance. In other words, we don't want threads that are contending for locks to be in a tight loop, wasting resources. It's better if they go to sleep and later get notified that they have a realistic chance of getting the lock. So we've seen examples of this, in particular in Java, with the stack TS, the TS again for thread safe example, and we use the waiting and notifying constructs that are part of the synchronization mechanisms that Java provides. The last example we saw went back to C. We looked at the multi-threading server, and this was the most realistic example, of course, because it mimics a production-grade web server. It doesn't have all of the features, it's not as efficient, but it does illustrate the one thread per request model that you'd find in a real-world web server such as Tomcat or Jetty. In particular, what the multi-threading server illustrates is the division of labor or separation of concerns that you'd want in a multi-threaded program. So in this particular case, the web server had a thread dedicated to listening for client connections. That was the main thread. And then request handling threads to read a client request and generate a client response. The very nice thing about this division of labor is that the web server is automatically more robust. For example, if a particular request handling thread should hang up, there's only one request impacted. So suppose, for example, that a bad request comes in, we pass it off to a request handling thread, and that thread's not able to read the request correctly or to process it and generate the appropriate response. Well, there's one request that's been impacted, but other requests that are being handled concurrently are perfectly fine. They're immune from the bad news that beset that particular handling of a request. On a multiprocessor machine, of course, this was not emphasized but was implicit. The the one thread per request model has the advantage that it can lead to true parallelism. In other words, you could have one processor running the listening thread and other processors running various request handling threads. So you get not only concurrency, but also parallelism. I'd like to make a final point about the multi-threading server. It's a point that will come up in the next series of examples. In the case of the multi-threading server, there was a method called handle request. So basically, when a thread executed, it executed, as you'll recall, the body of that function. And that function took an argument, basically the read-write socket that allowed the thread to talk to the client. So it took an argument, and it could have returned a non-null value, but didn't. And everything else was done in local variables. So what you had basically was a parameter plus local variables. There was no reliance on any sort of global variables. So in the jargon of programming languages, we were dealing with a pure function. And the nice thing about a pure function is that it is inherently thread safe, because every thread gets its own copy of local variables and parameters. If you've done some operating systems, you know that the local variables and the parameters are stored on the stack, or if the compiler is an optimizing compiler and a bit aggressive, perhaps in CPU registers. But in any case, it's up to the system, not the programmer, to make sure that the stack or the registers allocated for a particular thread are not stepped on by other threads. So the multi-threading server is idealized. For example, we didn't go against a database or do anything like that, but there were still some nice features in it. So that's a wrap-up of the most recent examples. This wrap-up will help as we move to the next series of examples. This lesson recommends two programming exercises. They differ in scope. The first is the more general of the two, and the second is specialized. The first involves C programming, and the second Java programming. Let's start with the first. It's very similar to an earlier exercise to improve the efficiency of the multiprocessing web server. In other words, this exercise is to create a thread pool, and the earlier exercise was to create a process pool. So very similar in spirit. Let me get into the details. One problem with the threading server is that on every request that comes in, the server creates a new thread, hands the request off to that thread, so the thread becomes the request handler, the worker, and once that work is done, the thread is destroyed. So that's the inefficiency, the creation and destruction of a thread per process. We'd like to fix that, and the way to do that is to create a thread pool at startup. So when the web server comes up, the thread pool is created. It would have some number of threads, whatever you think the average load might be. So for test purposes, 8, 16, something like that. And when a request comes in, a thread would be activated from the pool to handle the request. It would handle the request to completion and then returned to the pool instead of destroyed. Now, you can search on the web. There are a number of really fine implementations of thread pools in C, and finding one and using it would be a nice exercise in itself. If you have time, you might want to build the thread pool from scratch. So let me just sketch what the critical functions are for doing that. These are all, of course, library functions in the pthread library. So at the center, as you can see, is pthread cond wait. So this causes a thread to go into a quiet state, a waiting state, awaiting some condition. That's the first argument. I'll come to that in a moment. And the thread that goes into that wait state currently holds a mutex, a lock. And what pthread cond wait will do is release that lock. So the lock is released, the thread goes into a quiet state. It's very, very similar, by the way, to the Java wait call. So you can see the connection between what's happening in Java and the underlying C library. Now, a condition is basically an integer value. So for example, Here's one of the built-in conditions defined in the pthread header file. So the variable type is pthread_cond_t. Sample condition, the variable name, we initialize it to pthread_cond_initializer. But other values could be used. And the way you would awake a thread would be then to send a signal related to that condition. So for example, just as a general hint, your condition conceptually might be, this is the thread at the head of the wait queue. Let's wake it up and hand the job off to it. In effect, you're going to find, if you look at the online examples of thread pools, you're going to find application logic very similar to that. The second exercise is much more specialized, and it's basically to provide synchronization as a form of cooperation in Java. So the example is contrived, no question about that, but it gets to the heart of thread cooperation. So let me use this little depiction to define it. Let's say we've got an array that has 5 elements in it, as you can see here, and what we want to have are 5 threads, and each thread writes one letter into the array, and we want the letters to be in alphabetical order, A, B, C, D, E, and so on. So what I'm going to do in the code segment below is create 5 threads, but start them in the wrong order. So I'm going to start the E thread first, the D thread second, the C thread third, the B thread fourth, and the A thread last. What should happen then is that the E, D, C, and B threads should wait their turn until the A thread has done its thing. Then the B thread should do its thing, and so on until the letters are in their proper positions in the array. So here's a code segment that sketches that. As you can see, I've got an array of my threads, 5 of them, and down here I start them in reverse order, the last thread first, and so on. Each myThread instance of this class would have the following functionality. So you can see there's one and only one array, so we have the usual contention issue. I've also got a static integer variable turn initialized to 0. What that signifies is that the A thread should go first. So turn, as you can guess, is going to be updated as the threads do their thing. I then have a private integer variable ID. I have here some bad indentation. My apologies for that. I have a character variable C, so it's going to be one of those letters. And then the override basically is an infinite loop that calls write char, and I've not defined write char. Write char is going to need to be synchronized, obviously, because you can't have all of the threads writing at the same time. The idea is you would synchronize write char, and if the wrong thread, that is the out of turn thread, happened to grab the lock, you would put it to sleep. You would wait until the right thread grabbed the lock, did its thing. It would then wake up the other threads. So we've seen an example very much like that. This working file is exercise6.txt. I hope you have a chance to do at least one of these exercises, and if you have the time, maybe both. This lesson introduces another exercise on the threading server. We're looking in my Emacs editor at the source code, and at the top, I've put a little comment, a review of what's required for a race condition in a multi-threading context. And the answer, of course, is this. You need 2 or more threads executing concurrently with unsynchronized access to the same memory location. If you have that, you have the possibility of a race. Unfortunately, the threading server has a race condition, and the exercise is to diagnose it, and if you've time, that'd be great to fix it as well. Let me highlight the really important code. Down here at line 9, a pthread is created. The third argument is a pointer to the function that the thread's going to execute, and the fourth argument is the address of the client socket. So that's passed to the threading routine. Handle client is that routine, and as you can see, it takes one argument. It's a pointer to that client socket. The question is, where does the race condition occur? Why? and how would you go about fixing it? This happens all of the time in multi-threading programming, so it's a good idea to get some exercise doing this kind of thing. Best of luck.